Oh, great. So good morning, everyone. I'm not a real motivational speaker type, but good morning again. It's a pleasure to see everyone here, to welcome you on behalf of the Department of Mechanical Educational? No, Aerospace Engineering, that's right. My name's Stefan Smith. I'm the chair of the department, and it's a great pleasure to see you here. We have a program that I hope you'll find interesting, whether you're alum, staff, faculty, friend. And so I don't want to take too much time. I'll try and MC various things. We have initially some remarks from the Chancellor and the Dean. Then we'll have a little bit of history about the department and some keynote speakers, then lunch, and then we'll continue with the program during the afternoon. So at this point, without further ado, I will turn the podium over to the video of our Chancellor, Pradeep Khosla. So please listen to his remarks.
Hello. I'm Pradeep Khosla, Chancellor of UC San Diego, and welcome to the celebration of 60 years of innovation, impact, and community at the Department of Mechanical and Aerospace Engineering. I regret that I could not be with you in person to celebrate this great day, but I did want to take a moment to share my thoughts and my congratulations as we mark this momentous occasion. Today is a time to celebrate our shared history, and look ahead to an exciting future. And as we reflect on the department's journey, we are reminded of its early beginnings in 1964, when it was founded as Aerospace and Mechanical Engineering Sciences, or as we said, AIMS. This was made possible by the visionary leadership of founding chair Stanford S. Penner. Our inaugural faculty included experts from Caltech and UCLA, experts who laid the foundation for an interdisciplinary program that evolved into what we know today as the Department of Mechanical and Aerospace Engineering. Today, MAE is a powerhouse of innovation, with mechanical engineering ranking 8th in the US and 20th in the world. Our Jacobs School of Engineering ranks 11th amongst the nation's top engineering schools and 7th amongst public universities. These achievements are a testament to the department's commitment to advancing both mechanical and aerospace disciplines. Our faculty are enterprising. They're leaders who collaborate on groundbreaking cross-campus initiatives. They're global experts with numerous awards and accolades, including several members of prestigious national academies. And in collaboration with our outstanding researchers, they are tackling global challenges with unmatched expertise, from fusion energy to smarter grids, and from safer space missions to cutting-edge robotics. MAE engineers are driving solutions that make a real difference. And as we celebrate this milestone, we are grateful for the contributions of our esteemed alumni who have gone on to achieve great success in academia, in national labs, and in industry. Your engagement today is the key to our future success, and we invite you to enjoy reconnecting today with the people who make MAE exceptional. And we invite you to be part of our next chapter. Thank you all for being part of this great journey, and we look forward to building the next era of MAE together. And here's to the next 60 years and 100 years. Thank you.
Okay, so after these remarks, I will hand over the podium to the Dean, Al Pisano, who will offer his remarks. Thank you, Al.
Thanks, All right, it's obviously a friendly crowd. You applauded my ability to rise from a chair and stand behind a podium, and I'll take that. Thank you. It's hard in this political era to get applause for academia. Believe me, I appreciate every hand clap we're getting. Good morning, everyone. I'm Al Pisano. I'm the Dean of the Jacobs School of Engineering and have been since 2013, and I'm special advisor to the Chancellor. And a little later in my talk, I'll tell you where I failed in that role, a small failure, and I hope you get a good laugh out of it. I'm here to help you celebrate the 60th anniversary of MAE, and I want to thank everybody who's in the audience here with us today. Now, I think it would be silly to ignore the elephant in the room. These are stressful times. And as I go around the school, visiting every department 3 times a year, all 6 departments, and speaking with the chairs every month as a group and individually every 2 weeks, I am reiterating that, ladies and gentlemen, we have a job to do. Let's not get distracted by the chaos, or else failure is incumbent and our own fault. So today is a very special day for me because I am celebrating, and I hope you are too, the many ways that engineering education and engineering research leads to wonderful careers and improved lives. And I think we all need to make sure everyone remembers that. Stefan, thank you very much for the introduction. Stefan has been the department chair for 2 years and is doing a great job with the department. And I want to thank the chancellor very much for his remarks. But, and here's where I failed as special advisor, you know, you never want to think you can catch the Jacob School or the MAE department, catch them napping. Because in the 2 short weeks since the chancellor recorded this introduction, we are not 11 in the country, we are 10 among all engineering schools. We are not 7 among the publics, and I don't usually do this qualifier. You know, have you ever seen some dean stand up and say, I have the #1 engineering school in the country, where the chancellor has a green cupola over his office and marble stairs in front? Sort of like, no, we don't do this silly subcategories. We are 10 outright. There are no ties for 10. We are 10, and we are extremely proud of that. Well, if you really want to compare us just among the publics, yes, we're number 6, up from 7 last year. And aerospace engineering has cracked the top 20. They're ranked 18. Mechanical engineering is ranked 22. And most importantly, and I'll offer a friendly jibe to all the other engineering deans who don't vote us as high as we know we should be voted. We are the #1 public engineering school for other people's faculty citing our citations. So to all the other deans, I say, you may not want to call us top 10, but your faculty know that we are. All right, let's get that straight. We're also #2 public or private in the country for research effort measured in research dollars expended. And in fact, that means that this one school, all the departments combined together, are running $316 million a year in research expenditures. That is a lot of money per capita and a lot of positive impact. And remember, the majority of that money goes for student support. All right, so we are not wasting our research dollars. We are taking care of people, and we are helping those people create a better future for all of us. So I want to talk a little bit about research funding streams just for a bit. MAE is doing great, and I think I offer them kudos for their efforts here. But just for all of you who may not have thought about this as deeply as others might have, the funding stream to the Jacob School of Engineering, averaged over all the departments, is only 50% from the federal government. 12 years ago when I got here, it was closer to 78. Now it's only 50. The research pot grew, not because federal money went down. It actually goes up a few percent each year. It grew because corporate, private, and philanthropic funding sources have stepped in and recognized the value of the research that we do. So we are enjoying a balanced dual funding stream that enables us to fully engage the virtuous cycle between fundamental and applied research. I want to emphasize that we depend on both streams equally. The fundamental research is what you need to do to figure out what is the right technology to start bringing to market. And that's primarily funded by the feds. The privately funded research is the research that says, hey, it worked in the lab, how do we get it into the marketplace? MAE has a spectacular record of things going out into the marketplace. And as you talk to each of the faculty, and I encourage you to do that, they will all have a story of a success in that area. So, put another way, just in case, and I don't think I'm lecturing anyone here with this, okay? But I'm on a podium, and this is being recorded, so I'm lecturing someone. This dual balanced funding stream means that federally funded research advances the fundamental research to the point of breakthrough, and the industry money takes that forward to a mature technology that lands in the marketplace. And we've done a darn good job of doing that, and I don't see any reason for breaking that system. So notice, in this context, philanthropic money augments, does not replace, it augments the federal investments. Okay. Over my almost 12 years as dean, I have worked deliberately to drive us to this balance. And just last year, we achieved it. So, as I like to govern with mantras, and so one mantra I frequently offer is the great engineering schools of the next decade will collaborate their way to relevance. There's a lot packed in that one sentence. So if you want to be great in the future, you're going to have to take lots of partners, and you're going to have to do very relevant things. It doesn't mean you don't do the fundamental work. It means you do the fundamental work and drive it through the relevance. So, given all the headwinds we're facing regarding research funding, you can imagine this is getting more difficult to do, but I will offer to you that usually I don't lose sleep at night, but when I do lose sleep, it's worrying about how to keep the research funding streams balanced. This, you should ask around other schools you know. You're going to look far and wide before you find another one that's 50-50 like us. This is special, and we are not yielding this special balance without a fight. So I worry about how we're going to keep this symbiotic, this healthy symbiotic relationship between federal money and industry money alive. They depend on each other, and I can't have either one of them just walk away. So, we're working on a number of strategies to see what we can do to work with the situation. If you have ideas you want to share with me, I can assure you, any good idea I can get, we don't suffer from a not invented here syndrome. Any good idea you have, please let me know. So, let me pause on that theme and go back to something a little more relevant to MAE in particular. I was pleased that the Chancellor did cite that Ames first meant aerospace and mechanical engineering sciences, but a student of more careful history, more detailed history, would realize that there was a second Ames. Some people are nodding, other people are saying, like, what? Yeah, the second one was applied mechanics and engineering sciences. In either case, the foundation is clear. This has always been engineering sciences, which means engineering that starts from the deeper fundamentals and brings it all the way, brings those fundamentals through to the market. That is why this department has done so well for the last 60 years, and I believe it is the secret sauce that has fueled this department's ability to rise as it combines the fundamental and applied research in order to make itself truly relevant. So let me close by saying to all the founding faculty of Ames, I'm very grateful to all of you. We are standing on the foundation you built. Thank you very much. You built a wonderful and strong foundation. To the founding faculty of MAE, which is the third version, Ames 1, Ames 2, MAE, to the faculty who built that department, I thank you as well. You broadened and deepened that foundation, and you aimed it more and more toward engineering relevance. Oh, and by the way, one of the offspring of MAE is structural engineering, which is how shall I say, our sibling faculty, our sibling department. Thank you for all of you who were part of that. So, in final closing, I thank all the faculty, the students, the staff, alumni, industry partners, friends, and donors, supporters of all kinds who have made this wonderful department what it is and has made it worth the celebration that we are having today. Thank you all, and I'm looking forward to the next 60, because believe me, with the research in this department about biomedical, we all have a chance of getting there. Okay, thank you very, very much.
Thank you very much, Dean Pisano. So the next presentation is me. That's me. And I'm going to talk a bit about the history of MAE. And so I need to work out if this works. Let me see if I can get this to work. Does this work? Here we go. All right, so you've heard part of this already. I love this diagram. I first saw it at the celebration of the Jacobs School 45 years. So as the dean said, in 1964, there was the Department of Aerospace and Mechanical Engineering Sciences that then evolved to become, in 1972, the same acronym, which was KEY, apparently. And then we, in the MAE department, which is, you see, starts in 1999, view ourselves as the descendants of the Ames department. And I hope that the other departments don't view this as unfair. We view structural engineering and bioengineering as daughter departments, budded off. We view ourselves as the original. So you'll see that in 1994, a Department of Bioengineering was created. The Jacobs School was named in 97. In 99, there was the split. I came in 99. When I got a job, it was Ames, and the day I started my job, it was MAE. I was not consulted about this, but apparently my input was not required to make this change. You'll also see the Department of Nanoengineering in 2007, and then at the bottom we have the 6 current schools, 2 of which now are named departments, the Shuchen Jinlei Department of Bioengineering. It's a proud moment for a daughter department of MAE, and the Aiso Yufeng Li Family Department of Chemical Nanoengineering, named just last year. On the right-hand side, you see the other components of the Jacobs School, and my number one favorite name for department is Applied Electrophysics, and I'm only sad it lasted a few years, then became APIS, and eventually led to ECE and CSC. So that, I just love this diagram, and I have to show it. I don't apologize for that. So I'm going to talk a bit about places, programs, and people. I'm going to talk a bit about the physical history of the campus at UCSD. And my goal here is not to give a lecture in architecture, but to show you how an amazing institution place was created in 60 years. And it's really quite dramatic when you look at the campus then and now, to think of all the work that went into that, and now in a situation where we're going to continue into the future. I'll talk about programs. The dean already mentioned the current mechanical and aerospace engineering as our name. Those are our current BS degrees. And I'll talk about people, who are really the most important part of that, because without great people, the rest doesn't come together. All right, so the scan here is slightly iffy. This is from the general catalog, 1963 to 64. For those of you who are interested in these things, I highly recommend looking at all the scanned catalogs. The reason I like this catalog is on the right, you have the map of campus. I'm not sure this is going to light up that far away. Whoops, is it? Don't know. You can see, mostly it's Scripps, Institute of Oceanography. You can see what's called married student apartments, which are now coast apartments. And the campus right now is on the right. There are 3 buildings, Building A, Building B, and Building C. And there's La Horchels Drive, which intersects US 101. And if you want to really challenge yourself, try and work out what the road layout now is compared to what it used to be. It is not at all obvious. So we've come a long way since 1963. These are some pictures of the campus in the 1960s. On the left, you have Urey Hall, a building that is still there, and which was the original home of the Ames department on the 5th and 6th floor, I believe. And so that building I cycle by every morning. It looks exactly the same. This is the Geisel Library, being built in 1969. At the time, it was the Central Library. My colleagues who were here in the early days said, why did they call it a Central Library? It was absolutely miles off to the east on campus. Now it's the Central Library. We are, in fact, to the east of it. And on the right, an aerial view of campus that shows large amounts of unbuilt land. That tells you it's not what it is now. We have seen a lot of changes on this campus. I just love this. South of campus, that is the intersection of Gilman and La Horchels Drive without a bridge. Miramode Road on the right. Someone told me, my wife said, that looks just the same now. I'm not sure I agree with that. And the middle is an aerial view of campus. This is quite a challenge. Let's have a quiz for the audience. In what direction is the camera looking here? Any suggestions? North, south, east, or west? It is south. It is south. On the right, there's the Muir Apartments. On the left is APNM. And behind Muir Apartments, you can see the soccer field. That's now AstroTurf and the tennis courts. And near the crane, you can see York Hall. And you can see those parking lots that were there until about 6-7 years ago. Okay, so now let's move to the present. The MAE department now is essentially over 4 buildings. This is EBU2, which gets a big picture because that's essentially all part of MAE. And then we have the 3 other buildings, EBU1, SME, and Franklin Antonio Hall, which opened in 2022. And so this shows the campus's commitment and efforts to growing the engineering enterprise, and in particular the Dean's efforts, and I would say Associate Dean Tynan's efforts for Franklin Antonio Hall, which I encourage you to visit if you haven't seen it before. It's a very interesting building with a wonderful view over the campus. All right, so now we have a campus that has grown with these wonderful buildings. What about the programs? Okay, so some more history. I went to the Geisel Library on Tuesday to look at the special collections, look at the archives of Ames. Very interesting. So Ames started off with a BA in Applied Sciences bracket mechanics, and I'll spare you the details as to how that transformed itself into an engineering degree. The 2 majors that we have now are mechanical engineering and aerospace. The mechanical engineering was created in 1984, accredited 88, and the aerospace engineering in 1993, accredited 2005. And on the way, there are a number of other degrees that came and went. Some moved to other departments, some were discontinued, and we've reached a very pure mechanical and aerospace combination now. In the past, we had the applied mechanics degree, engineering sciences, environmental engineering, and I will point out that environmental engineering is now an optional track within mechanical engineering. It's an important part of the research in this department, and you'll hear a presentation this afternoon about energy and the environment. Finally, the chemical engineering degree, I have to name that because one of our keynote speakers has a degree in chemical engineering. Started in 1979. It was the first program that was accredited in engineering, well, in mechanical engineering in Ames department. Became a program, then moved to nanoengineering, which became the chemical and nanoengineering department. So that, for those of you who like administration, that is the history of the various majors. So this is fun. This is the 1964 catalog, and this is the first time you'll see the words aerospace or engineering. And you see that in first college, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 9 department chairmen. It was a different era. And we have SS Penner, PhD. At the time, there was a Department of Earth Sciences, which actually doesn't exist anymore. So this is actually quite confusing if you look at it. And on the right, in the 1965 to 66 catalog, we have the first Ames classes listed on the catalog. And you'll see some real classics like Ames 101, Ames 102, Ames, so on, that still exist. They become MAE 101A, 101B. Some of us in this room have taught those classes, and we are the proud successors of the 1965 to 66 instructors of this program. It's very interesting to see the classes that existed at the time. Fluid mechanics, complex variables math 120. We don't take that anymore. All right, graduate degrees. And I'm going to come back slightly later to the interaction that the dean mentioned about we have undergraduate, graduates, and research. So we have an MA and PhD programs. We have a Convergent Systems Engineering program, MES program. We have a graduate program in material science that will be mentioned this afternoon in terms of materials. That is a multi-department program that has its own graduate intake. And we also have the Applied Ocean Sciences graduate program joint with Scripps Institution of Oceanography, which is a very interesting program. And on the left is the approval letter from Chancellor Atkinson for the program in 1980. I love these kind of old files. They've got stamps on them. And on the right, this is one of my favorite things ever. I found it in the Third College Thurgood Marshall records, but I've seen this somewhere in the department, and some of you in the audience will have seen it before. It's the graduate program brochure. Given that it says Aerospace and Mechanical Engineering Sciences, it must have been between 1962 and 68. And I've just shown you the first and last pages. The last page is Urey Hall and a map of where the campus is, which is particularly nice. I didn't show you the other pictures inside, which have photos of the faculty. And the last slide, I'll show you one picture because I couldn't resist it. So this very strong graduate program that started way back in the 1960s. All right, the dean has emphasized the importance of fundamental research leading on to market. And here I'm really focusing on the fundamental research. Maybe that's my own prejudice. We cover all areas of aerospace and mechanical engineering. We have fluid mechanics. I put the word classical, that doesn't really make sense. I just mean standard fluid mechanics as opposed to environmental fluid mechanics, combustion, any of the other add-ons. We have solid mechanics, mechanics of materials. We have plasma physics, which is quite unusual, but has been a key role in understanding energy and engineering processes leading into the current fusion engineering initiative. We have a very strong controls and dynamics programs, and that is interesting historically because there was one right from the beginning of the department, and then it left, and then it came back and was reformed by Bob Skelton and has now remarkable controls and dynamics groups, which I think is a key aspect of the department. On campus, there are also organized research units. These are structures to look at particular research areas, and there are a number that are very much linked with the department. There's a Center for Memory and Recording Research, CMRR. There are some pictures later of that. And the Center for Energy Research, that goes back to 1974. Those are both very interesting. CMRR was started with close links with industry. Frank Talke is here, so that's a very interesting model. And the Center for Energy Research, if you look at the date 1974, was during the oil shocks and energy crisis of the 70s, when Sol Penna became interested in energy as an engineering question. How does one think about it in terms of systems, in terms of measuring metrics of quality of life and so on? And then there are other, I haven't put a whole list of other centers in the school. I just mentioned the Contextual Robotics Institute, which I think has been very helpful in bringing together faculty across multiple departments in robotics, which is very exciting on the student side and also in terms of research. And I'm just showing the funding agencies that we're familiar with that get a lot of funding for the department: the National Science Foundation, NASA, Office of Naval Research, Department of Energy, National Institutes of Health, and so on. I haven't got a list of all the corporate sponsors. Okay, so we have this structure, we have buildings, we now have programs, and we have research. So what about people? So I want to talk briefly about people, and then beyond this, it'll mostly be photos. But I think photos are really important to see our colleagues, to remember them, to see how they were maybe a few years ago. And in the audience, I hope that some of you will recognize some of your former instructors and professors. So the faculty are remarkable. The easy part of my job is the faculty do everything in such an incredible way. They have awards, as the dean mentioned. They're great teachers. The students and alums are also remarkable, so that's one particular reason I'm so pleased to welcome many of you here today and to hear from our keynote speakers. And I also want to give a shout out to the staff. A department like this, a university like this is not possible without a lot of hard work from people who work in financial affairs, in academic personnel, human resources, student advising, faculty assistants, research management, and laboratory engineers. So very important part of the department. And I know that in events like this, we tend to look at old photos and buildings and archives, but the staff have been a critical part of the department ever since it started. And in fact, one of the archives, I found a letter from the Vice-Chancellor to a staff person in Ames saying, "I hear you were sick yesterday. I'm so sorry to hear that. It's the first day you've missed ever since you've been on campus." So they was really paying attention, saying, "I hope you're feeling better." And then, of course, this MAE enterprise falls within the Jacobs School, within UC San Diego and the whole San Diego area. And I think it's very important to build up links with the community and to work with the deans and administration who have helped us get to this position. All right, so now it's mostly going to be photos. You can wave at your former professors. This is Sol Penna, the founding chair. This picture, my guess, is taken in the late 1990s. You've got a clap for Sol. It's a rather somber picture. This is Paul Libby, who was another founding member of the department, who was a later department chair, and lived to be over 100, which shows that being an Ames faculty member is good for your health. Here we have, and Dave is in the audience. Dave, I think the year is wrong there. I don't think it's 1970. I think it's 1991. Can you correct that, Dave? Is that 70 or 91? Not sure. Paul Libby and Harold Sorensen. Harold Sorensen was an early controls participant and was also helped start what then became the MAS program. So some of these pictures, we have Sol Penna again. Robert Roberson was a department chair, and Dan Olfey, who I don't think is with us today, but is still in the San Diego area. We can keep the claps till the living people. Chuck Van Atta was a very remarkable fluid dynamicist. The beard was quite horrendous. I'd never seen that one before. Carl Gibson, many of you will remember, a very long-time colleague, passed away a few years ago, last year. And Alan Schneider, who was here when I arrived, was also a very charming and lovely man. So I think they get an award. Absolutely, they get a clap. And then we have Foreman Williams, John Miles, and Y.C. Fung, Bert Fung. So Bert Fung was founding chair of founding department member of bioengineering, but a very important figure in biomechanics and bioengineering, so I included his photo. Foreman Williams still comes into the office on a regular basis, and John Miles, for those of you in fluids, holds the record that will never be beaten of JFM papers. Okay, so now some more recent pictures. Some of these are a bit fuzzy. We worked with the scans we had. This is Sol Penna's 90th birthday. You can see an array of department chairs. The late Juan Lacheras, Frank Talke, who's in the audience, Vitaly Nestorenko, Sultan Usaka, and Sol Penna. There seems to be a monotonic gradient going down from left to right. So I'm very grateful to them for all their efforts as chairs before my time. They're wonderful colleagues. And these are some very distinguished colleagues of ours in solid mechanics and materials. I won't read all the names. Some of them are still here, like Frank. Some have passed away, unfortunately, and some are now retired, but it's always fun to see their photo. I do not know when that photo was taken. Frank, do you know when that was taken, that photo? I don't know.
What did you ask me?
When was the photo taken? I don't have a year for that one.
Oh, that is hard to remember now. Looks like late 80s.
Sometime in the 80s is my guess, yes. Because it's after CMRR. Yeah.
Yeah, that is maybe 89 or
89, okay, all right. That's a very nice picture. Then we have Frank, Sia, and Dr. Tan. And this is a picture of CMRR with Vlado and Frank and a bunch of students. This is a more recent picture, 2012. It's very nice because it has on it Juan Lacheras, as I said, who was a very important member of the department, a chair who passed away very tragically during COVID. We have Professor Jimenez from Madrid, who was a Penna lecturer. So Sol Penna endowed a lectureship, and it's always very nice to welcome these very distinguished speakers. And Professor Marsden and Del Alamo, unfortunately, are no longer in the department, which is very sad. They were wonderful colleagues. Here we have a hiking shot, Frank and others. And this is the, I don't know who sent this picture to me. I think it's my favorite picture. This is Professor Delson when he was a student working on an Ames 156B project. He looks very happy down on the beach. Some more recent pictures. This is the launch of the CIMA Center for Control Systems and Dynamics. You'll see, I won't go through the names of all the faculty. There's quite a few of them there. This is some work from Farhat's group. And this is Carlos Coimbra, our colleague, receiving a distinguished chair. Picture of me and the dean. And here we have Jorge and Sonia. Oops, I misspelled Sonia's name, I'm sorry. And then on the right, we have the Pisces experiment. So this is a plasma experiment down in the basement of EBU2, run by George's group. This is Miroslav lecturing. That's a great picture. Miroslav, it's a fantastic lecture here. It looks really good. And here we have a picture of MAE 20. So here's an actual classroom. This is during fall 22. A lot of masks. This is Dr. Evdokimenko, who's teaching the class. And this is Professor Rosengren giving a talk at the Amos conference. My guess is that's in Hawaii. Is that right, Aaron? And this finally is the MAE Autonomous Vehicle team, a picture from Jack Silberman. I may have misspelled their name, but they are doing very exciting things, full of energy, and it's great for the department. So let me talk a little bit more to finish up. So don't worry about the picture of me. I just want to once again point out the importance of the staff and to thank you for their help today. So everyone wandering around in a T-shirt, an MAE 6th anniversary T-shirt, has been helping out and done some amazing work, in particular Katie, Samantha, and Ceci. So I'd like to thank them at this point. Thanks so much. So now let me sort of kind of wrap things up after the pretty pictures. So MAE is a department in an R1 university, a very large research university. I have the updated numbers, unlike the Chancellor, that's right. And as a department in a large research university, MAE has a unique role, and I'm going to talk less about what the Dean was saying about the funding streams, but more about this overlap, I'd say the synergy between research, fundamental and also leading to market, graduate training. So we have these remarkable PhD students, also postdocs, who are there working with faculty as part of their educational and career development. Some may become faculty, some may move to industry. And then also undergraduates. The whole goal of a large university or an university is to train to teach students. But this synergy with the research, the faculty, the graduate students, undergraduates, I think is extremely important. And I hope it's something that we can continue. I think it's a very important aspect of our mission as a department. And I think it's something that we do quite well. As you saw in that evolution of degrees, the educational programs become broader. We started as a very strong engineering science department. I think you can now look at the program and say that it's a balanced program that spans fundamentals in science, but also things like capstone design projects, laboratory projects. But the goal is still the same, to make sure that students come out with a strong grasp of basics, ready for whatever they're going to do that's going to be so amazing, whether it's in industry, whether it's research. That's the fundamental goal. And finally, as the Dean says, the research enterprise has become broader and larger. So that, I think, is an exciting aspect of the department's evolution. All right, so what about today? So today's a chance to welcome people back and to hope that you enjoy seeing what the department is up to. Tell you a bit about the department now. That was my little historical review. We're going to have some presentations this afternoon about the future of engineering and how MAE is well placed, is thinking about these aspects. We're going to have an alum panel that will talk a bit about their experience in MAE, so I'm very thankful for them to coming, and we'll have some presentations from our alums also to tell you what they've been doing. So to conclude, the last 60 years have had obstacles and challenges, and I think our predecessors have met them with lots of creativity and determination. I think the goal is to continue in the grand vein that they pioneered and to move forward to deal with the obstacles or the challenges in front of us with resilience, with energy and with enthusiasm. So thank you very much for coming. I hope you enjoyed learning a bit about the history of the department. And now we'll have a little break to get things sorted out, and then we'll move on to our keynote speaker. All right, so thank you very much. All right, I think we're going to continue with the next item on the agenda. Lieutenant Burnham will give us a talk, and I'm going to pass the mic to you. Let's give a welcome to Lieutenant Burnham, by the way.
Hello, everybody. I'm Denise. I graduated in 2007, and I'm going to be chatting about my path to becoming a NASA astronaut. All right, it's 2003, and I walk onto the UCSD campus. I'm a chemical engineering student. Now, you heard when I was a student here, we were underneath the Mechanical and Aerospace Engineering Department. That's why I'm speaking to y'all. I was really excited to start my journey. This is Argo Hall over in Revelle. For those of you, I guess I'm just trying to think the best way to describe Argo. I was not a Revelle student. I was actually an ERC student. This was our overflow housing, and we were all living on the 5th floor. One of my absolute best friends in college, Irene, she was an aerospace engineering student, and she lived on the 5th floor of Argo Hall with me. Neither one of us had cars. So, this is a very big campus. It's a lot bigger now than it was when I was here, but it still was quite large. And we spent a lot of time walking around this campus and just sharing our goals, sharing our dreams. And we actually had some shared dreams. We both wanted to work for NASA. We both absolutely adored space exploration. I wasn't sharing my childhood dream of becoming an astronaut, but I was unclear on the path that I would take to get there. While I was a student here, I did intern with General Atomics, and I also spent some time in a medical research lab. But after those experiences, I was like, well, what should my exact path be? I knew I just wanted to be an engineer, work as an engineer. I wanted hands-on experience, but I also had a love of adventure, and this is going to totally make sense. This is a big leap. In my senior year, I signed a contract to work on an oil rig in Brazil, and so I was super excited. In reality, I was sent straight to the Arctic, and more specifically, that is the flight from San Diego to Dead Horse, Alaska. It's 2007. Welcome to the Arctic. It's incredible. This is the slide where I was initially planning on really building it up for y'all, but I have to say it was super foggy in San Diego this morning, super foggy yesterday, and so it's going to sound slightly less dramatic, but here we go. I don't know if any of you remember, there was a screensaver. It was a Windows 95 screensaver. It was known as Starfield. That's exactly what driving at I was going to say at night, but it doesn't matter, right? It's wintertime in the Arctic. It's dark all the time. It's what it felt like driving there. There are no trees. It's extremely dark, and there's only wind. The snow comes at you from every direction, just like you're in the Starfield simulation. So now I'm going to kind of talk about just trying to build the mindset of, like, this is my first job out of college. I did not see oil rigs in San Diego. Oil rigs are very complex. They are fast-paced and high-consequence operational environments. For the rig crews, for a lot of the guys, this was the jobs of their fathers and their grandfathers, and they took a lot of pride in doing a good job. And just to kind of further build some of this environment for y'all, everyone has to work and live together. You are in the Arctic, after all. There's literally nowhere else to go. You work a long shift. It's a minimum of 12 hours a day, every day, consecutively. There's no such thing as weekends or holidays. And I've done it for 6 weeks at a time. You get a couple days off, and you go right back to the Arctic. There was a big learning curve, and kind of looking back at these moments, they were really critical on my path. They tested my resilience, and they helped me develop a deep respect for the process of becoming. And you may be wondering, like, what does that mean, process of becoming? Well, you may have heard that working as a high-functioning or becoming one team is critical for, like, the success of an operation. But what does that process of becoming that high-functioning team actually look like? That's where you have to earn it by living it and doing it day by day. You know, there's some hard lessons to be learned. There's one other kind of comical thing I wanted to point out in the photo in the bottom middle there. So leaving San Diego, we don't own proper winter gear. I had exactly 2 sweatshirts that I owned. I happened to be wearing one of them in that photo. You can see the R in university poking out through my coveralls there that I bought from the Price Center there. And that's actually me in North Star Island in the Beaufort Sea. It's a marginal sea of the Arctic Ocean. All right, kind of further building the environment, right? So I talked about the complex nature of having an operational environment. That's your first job out of college. Very, very different culture, but also some of, like, the lighthearted parts about it, right? So that's the outside air temperature gauge, negative 28 degrees Fahrenheit. That's considered a warm day in the Arctic. So I already let you know my suitcases were not properly packed. When people tell you to keep your head on a swivel and watch out for animals, unfortunately, they are not talking about penguins. And when people say, hey, there's bears, they are talking about polar bears. This is a picture of some muskox. You already saw the little foxes, and they're adorable. However, I mean, like, look, I didn't fact check some of this. I was straight out of college. They told me 9 out of 10 foxes up there had rabies. And so I'm like, what? Where am I? So one other kind of thing I wanted to point out, right? So you have your head on a swivel. You're in this fast-paced environment. It happens to be a very remote location, extremely cold, dark. You got to watch out for animals. And what are the chances that the engineer that I was assigned to first learn from, he was from Brazil? It blew my mind that we both got to freeze there together. And in the top left, that photo is actually the only palm tree I was told I would be seeing in 2 years. So there's something that we would do, which I'm sure it's going to seem super great. We would put on all your gear, and you would take a photo, and you could send it to anybody's family because you can't really tell who's in the photo. So this actually happens to be me standing in front of the Trans-Alaska Pipeline in my Arctic gear. And it turns out it is not so different than what I can do now. You just gotta drop the visor, and we call this a hi mom. You could send it out to anybody's family. As I'm kind of describing this path, and I'm going from the Arctic, I have 10 more years of experience on oil rigs. I become a well site leader. I get to have these really amazing operational experiences traveling throughout North America. Obviously, I have go to graduate school. I commissioned as an officer in the Navy. These are all really important experiences. My former commanding officer is actually in the front row, and I just wanted to have to say that I appreciate the support. These are tremendously important experiences, but I'm gonna shift the focus in the story now. So I'm not gonna talk about those paths, but what I wanted to kind of say is when you are applying to become an astronaut, there is just a certain minimum requirements you have to meet. You have to have a STEM education. You need at least a master's degree and progressively responsible experience. That is it. It is literally that open-ended. And so now I wanted to kind of demonstrate, or at least show to y'all, how I approach the rest of that open-ended application. If you can make it through this without getting motion sick, congratulations. You could add this to your NASA application. But more importantly, I didn't want anybody, or at least I wanted to invite you to not focus on the details of what that I'm doing, but more so feel the pace, the cadence of kind of these flashing moments like that are my hobbies. I spent a tremendous amount of time away from home on oil rigs, and my days off were very precious to me. I was very intentional about how I wanted to spend my days off. And I would set these goals. And I don't know if you caught it, but my other mentor, Dr. Al's in the audience, and it does kind of crack me up. He was the one that suggested that I do scuba diving in Alaska. Oh, it just flashed through right there, me in the dry suit. Great experience overall, but you'll notice that is the only photo of scuba diving. Everything else is centered around flying. You kind of learn those hard lessons. Yeah, so this should be wrapping up here shortly, but I did want to kind of say, how do you take all these experiences, kind of bundle it up, and convince NASA that this is a worthwhile way to spend your time? For me, I had a lot of practice. I first had to convince my mother. So this is a photo of me and my mom. It may have flashed through with us actually flying together. And this is an amphibious aircraft. It has retractable landing gear. We took off from land, retracted the gear. I took her out to Lake Berryessa, landed on the water. And for my mom to actually accept flying with me was actually a very special moment. It was a very pivotal moment, right? You could imagine when you're first driving with your parent and they're terrified and they're holding on. But I asked my mom, we were both shocked. I'm like, hey, Mom, you should go flying with me. And we were both just as shocked that she agreed. And I am the youngest in my family. And of course, I have to find a way to kind of, slightly blow a special moment. This was just my pure joyous expression of successfully reenacting this lost key routine where I act like I dropped the keys and I have to jump into the water. But ultimately, her agreeing to go fly with me did give me a tremendous amount of confidence. So NASA put out a call for a new class of astronauts in early 2020. There were over 12,000 applicants, and this was my third time applying. The first half of 2021 was reserved for on-site interviews at Johnson Space Center. There were multiple rounds, and in October of 2021, I received the news that I had been working on for many, many years. I had been selected as a part of the newest class. Thank you. And just, you have to understand, like, the phone call that you get, it was kind of funny to me. It was the chief of the astronaut office at the time, Reed Wiseman. He's currently the Artemis II commander. And it's super casual. It's just like, hey, I just wanted to know if you're still interested in joining us. And I was like, what? Yeah, like, of course. So, of course, this is the culmination of many years of hard work, dedication, and there is luck involved. NASA selected 10 astronauts, and you can see there's 12 of us there. We were joined by 2 international partners from the United Arab Emirates. We all have a really diverse mix of backgrounds. In this photo, you could see there's scientists, there's test pilots, medical doctors, and of course, engineers. And the really kind of amazing part of everybody having a very different background is you all have to come together. You receive the exact same training during this 2.5 year period, and you all contribute your skills towards a common mission. I'm going to spend a little bit of time now just kind of chatting about what that 2-year training period looked like for us and kind of what were considered the key areas of the candidate program. All right, the International Space Station. So the ISS is a partnership of 15 countries from 5 space agencies. 2 primary languages are spoken on board, English and Russian. Russian is actually one of our key areas that we have to learn. You have to be able to read, you have to be able to speak, as well as understand. The ISS itself is a national research lab in low Earth orbit. It's at roughly around 250 miles altitude, and it's orbiting the Earth every 90 minutes. It has been continuously crewed for the last 25 years, and it's typically around a crew of 7 people for 6-month missions that can be extended for up to a year. And the planned operation is through 2030. This is Building 9. This is what the modules look like in Building 9, where we learn to do the maintenance of the ISS itself. And just to give you an idea for scale for the volume, it's roughly the size of a 5-bedroom house. So another key area of our training is robotics. So the robotics operations, it focuses on the Canadarm2. The middle photo there, that is me in Montreal training with the Canadian Space Agency. The best way to kind of describe this training, it's like a high-stakes video game. The left and right images, when we're training, you have a visiting vehicle that comes, and it's carrying critical supplies that's needed to resupply the ISS. That vehicle will come and hold at a certain position, and it is your job to operate the arm and go capture it and have it berthed to the ISS and then retrieve the supplies. Another task you might be asked to do with the robotic arm is when a crew member is conducting a spacewalk, they might be on the end of the arm and you have to move them into position to their work site, but there's a lot of tricks to that. You have a very limited amount of cameras, and whenever you're trying to position to a different camera view, you have to make sure that you are not running the arm into the structure, or you're not running the crew member into the structure, so you have to use the parallax, kind of making sure that none of the camera views are converging. So EVAs, or extravehicular activities, this is our spacewalk training. So the middle photo there is kind of showing the position of being the suit IV. You might be tasked with suiting somebody else up for the spacewalk and kind of getting the airlock prepared for them to exit. And kind kind of on the ends there is when we get suited up and we have to learn all about how to operate the systems of the spacesuit itself, how to kind of fly the spacesuit, and this all takes place in the neutral buoyancy lab where we conduct our training. The NBL is one of the actual largest indoor pools in the world, and it holds over 6 million gallons of water. This is just a short clip of what it's like to get suited up. The suits are super heavy, and they are sitting on a donning stand. You get hoisted into the water. There's a set of divers that are assigned to kind of not only be safety divers, but they also are responsible for weighing you out to kind of simulate the actual spacewalking environment. You're not using your feet, obviously. You have to use your hands. These are pressurized suits. You're having to translate along the truss, working with different tools. And these runs last about 6 hours. You have no food in that time period. You have a drink bag that sits at your chest that has like a bite valve kind of hanging off to the side, and that's it. You know, the best way to describe that training is you have to be comfortable being uncomfortable. All right, aviation. So if you don't have a military background, you get sent to the T6 training in Pensacola with the Navy. So the non-military aviators go spend a couple months there where we get checked out to be in the back seat of the T6. And then when we get back to Johnson Space Center, NASA keeps their T-38s at Ellington Field. And for that training, you get through the syllabus to be rear cockpit qualified. You work with other, you kind of get to rotate through other astronauts in the office, getting to train together, spaceflight readiness training, crew resource management, kind of making these fast decisions. But ultimately, those decisions have real-world consequences. These are ejection seat aircraft, and currently I have over 200 hours in the T-38. Expeditionary skills is kind of like the final kind of core competency of the candidate training. The top middle photo best describes expeditionary skills. In that photo, you see 8 adults splitting a singular cookie after hiking 50 miles in Wyoming with frozen socks. Welcome to expeditionary skills. The top right is the survival training we have to receive with the SEER instructors in Fort Rucker in the Army. And then the bottom photos are showing the geology training we get to kind of go out to different sites where they, like a world-class geologist kind of teach us all about either lunar geology or it could be just terrestrial as well. Ultimately, these are the trainings that we receive where we're outside of the classroom environment, getting to take care of your team, but also just in general team building opportunities. All right, so what is next? Our class graduated in March of 2024. We all work various ground jobs supporting current and future NASA missions. Right now, I am the current increment lead for the onboard crew, meaning we are their advocate. We're just making sure that between the ground and the people on board, that they are being taken care of. And we are all, as a class, eligible for mission assignments. Our first classmate is actually in space right now, so at least the line is moving. So the training never ends. Even though you have a ground job, you are still responsible for maintaining your Russian language skills. You have to still maintain the proficiency in your NBL runs for the spacewalk training. You're still flying in the T-38. But in addition to that, you get other unique opportunities that you can participate in. So you might be flying in a helicopter, the high altitude training with the Army National Guard. Sometimes you are being hoisted in a helicopter as part of the underway recovery training, testing, and validating procedures for the recovery of the Artemis II crew and the Orion capsule. That actually just took place a couple weeks ago in San Diego on the USS Somerset. And you might see me there in that one photo in the fume hood. Ultimately, as an astronaut, you are an operator. You may have the privilege of carrying out an experiment that's representative of somebody else's life's work. And we take great care in making sure that we are always trained and ready for whatever we're asked to do. We also support our colleagues for their space launches. I got to travel for Don Pettit's launch to Baikonur in Kazakhstan for his launch on the Soyuz last September. So this is his launch, and I actually reached out to Don, and I said, hey, he's on the ISS still right now. Do you mind snapping a photo of San Diego for me? So Don's an incredible photographer. He's going to be coming home here in about 10 days or so. This is what San Diego looks like from the ISS. Have to say we look pretty good. Just wanted to leave y'all with one final story where I kind of bring it all home. So in 2022, I am in my first year as a candidate with NASA. And we're based out of Johnson Space Center. End of the day, about to go home, step into the elevator. Yes, astronauts don't always take the stairs. Riding the elevator down, the doors open, we're roughly halfway through the building, and I hear, hey, Denise. Just like that, I'm 17 years old again. What are the chances it was my friend, Irene, from freshman year, Argo Hall, 5th floor. We both made it. I don't remember the day-to-day of my time here. Unfortunately, it's been too long. I graduated almost 20 years ago. But what I do remember are the people. I remember those shared experiences. I remember cheering each other on, dreaming big. That was my main takeaway, I think, from my time here. Congratulations on 60 years, and thanks so much for having me.
Thanks so much, Denise. That was amazing. One quick comment. Our colleague, Professor Foreman Williams, and other scientists with him sent some missions up on the space shuttle to do combustion. So there are UCSD experiments that were done in space by some of your predecessors. Okay, I think we'll move on to the next presentation. Dr. Tammy Ma, who will be telling us, I assume, a little bit about fusion. Dr. Ma is a PhD graduate of this department, and it's a great pleasure to welcome her here again.
Thank you so much. All right. Good morning. Thank you so much for the invitation. Fiat Lux, the motto of the University of California. Fiat Lux, let there be light. And I cannot think of a more fitting expression for how the University of California, San Diego's Mechanical and Aerospace Engineering Department did exactly that, illuminating the course for me to get to where I am today. I received my PhD here from UCSD in 2010, where my research had me playing with light itself. I studied how ultra-intense beams of laser light interact with matter. And this then led me to the Lawrence Livermore National Laboratory, where today I am a physicist that gets to play with the biggest, most energetic laser in the world. And when I say big, I mean big. This laser has 1,000 times the power of the entire US electrical grid. And what are we doing with this laser? Well, we use these enormous beams of light to compress little balls of hydrogen. Hydrogen, that very first element on the periodic table. By compressing and heating these balls of hydrogen until they fuse, we can mirror the same reaction that powers the sun. Essentially, we are creating miniature stars right down here on Earth and lighting a path toward harnessing fusion energy. Fiat Lux. Okay, let's talk a little bit about fusion. What is it and why are we pursuing it? Fusion means unlocking a different kind of nuclear power. Instead of splitting big, heavy atoms like we do in fission and the nuclear reactors we have today, fusion brings together two atoms of a light element. In our case, we use isotopes of hydrogen, heavy hydrogen, called deuterium and tritium. Our giant laser pushes these hydrogen atoms close enough together at hot enough temperatures and holds them together long enough that they merge. And as they do so, they become a helium nucleus, which, it turns out, weighs just a little bit less than that deuterium and tritium originally did. And that little differential in mass makes all the difference. You know that equation on there, even the kids. This is Einstein's famous equation, E equals mc squared. We are interchanging mass for energy, a reaction that releases truly enormous amounts of energy. Okay, how enormous? 1 single pound of fusion fuel equals the amount of energy in 5,000 barrels of oil, or 3.5 million pounds of coal. This is the ultimate energy source, not least because the fuel that we need for fusion is abundant. Approximately 1 in every 7,000 molecules of seawater is D2O instead of H2O. And we know how to make tritium from lithium. So conceivably, we actually have enough fuel for 30 billion years of human use at today's level. That's what I call energy security. Fusion is also clean energy. In the reaction, a deuterium plus a tritium yields a helium. Carbon is nowhere in the equation. Fusion is also inherently safe. To get fusion going, you have to put enough energy into the system to drive the reaction. If you ever want to stop fusion, you just cut off the initial energy source. You'll never just have runaway. Now, fusion will generate waste, but it's not the kind that remains radioactive for tens or hundreds of thousands of years. Instead, the low-level nuclear waste of fusion will decay away in just decades. That means a fusion power plant can be placed nearly anywhere, with energy production near big cities, and it would easily fit into our current grid infrastructure, or even the smart grids of the future. Fusion can also provide flexible energy when you need it and in different forms, electricity for our homes or high-temperature heat for industry. Now, to be fair, there are a couple of drawbacks to fusion too. Fusion is incredibly complex and incredibly difficult. To develop fusion has been and will be expensive. But the potential benefits of fusion are so great that it is worth it. So, how do we make this all happen? Well, that's what we've been working on now for over 60 years, about the time that the MAE department has existed here. So let's go back to that ginormous laser I was talking about. This is called the National Ignition Facility, or NIF, at the Lawrence Livermore National Laboratory in Northern California, about 50 miles east of San Francisco. The NIF laser is housed in a building the area of 3 American football fields side by side and 10 stories tall. And if I take the roof off of the building, I can give you a look inside, and you'll see that the building is filled with thousands of giant optics. And in fact, the NIF is not just one laser, it's actually 192 separate lasers. Each one alone, one of the most energetic in the world. We're going to combine 192 of them to all shine down on a tiny fuel target, about the size of a peppercorn. Okay, let me take you into the facility to give you a closer look. The way it works is the laser is going to start out as a tiny pulse of light with just the fraction of the energy of a typical laser pointer. The beam's going to divide and then bounce back and forth across this very large facility, passing through slabs of glass that boost up the energy of the laser beams. In total, each laser beam will travel nearly a mile while it gets amplified up 1,000,000 billion times and get expanded in size from a tiny pinprick to over larger than a square foot. These 192 super powerful laser beams are then all going to be brought together, directed into a spherical fusion chamber. Half the beams will come in from the top, half from the bottom. They're going to blast their concentrated light onto a tiny canister that sits right in the center of the chamber, which is about the size of a pencil eraser. The canister is going to turn this laser light into an energetic oven of X-rays. And these X-rays are so intense, they're going to start to blast off the surface of the little pellet that sits right in the middle. At the same time, by an equal and opposite reaction, the rest of the capsule is going to squeeze inward, and we generate conditions hotter than the center of the sun, with pressures seeming like 180 million Earth atmospheres pressing down on you. And if we do it right, what we get to do is start a little fusion burn. We spark a burn right in the center of that capsule, and it burns through the rest of the fuel. We generate, essentially, a miniature star here on Earth. And if we do it right, what that means is more energy out of the experiment than we put in. So clearly, this is not easy. This is a story that bridges enormous scales, the temperatures and pressures of a star focused in on the atomic level. Remember how I said our laser is 1,000 times the power of the entire US electrical grid? Well, you guys all had a great education here at UCSD. Power is defined as energy per unit time. So what we're able to do is take huge amounts of energy and compress it down into just nanoseconds. And that's why the lights don't flicker across the globe every time we take a shot, even though we are able to generate temperatures that are the hottest in the entire solar system. Okay, so I know this all sounds a little bit crazy, but that's okay, because I'm not the only crazy one. Right now, there are tens of thousands of scientists and engineers all around the world working on different ideas for fusion. Not just using lasers, but sometimes using things like giant magnets to shape and control the fusion. These experiments have cool names like tokamaks or stellarators, and there's many more ideas as well being pursued by a myriad of startups all around the world. It's a whole host of smart, talented people, including right here at UCSD, working to make this dream a reality. And it won't surprise you that UCSD also plays a very consequential role in this field. A team of brilliant faculty have long spearheaded the charge in plasma physics, material science, and fusion innovation. Just this year, a new Fusion Engineering Institute was stood up, bringing together engineers, physicists, computer scientists, and fusion experts to tackle the most difficult fusion engineering challenges. This institute will position UCSD to be one of the leading institutions translating fusion science into safe and abundant clean energy for California and the world. And UCSD has long collaborated with Lawrence Livermore National Lab, where I am now, where work in fusion has been ongoing since 1960 to support national security. We need to understand fusion in order to understand how the US nuclear arsenal can remain safe and effective. And that has actually provided the stable funding required to pursue this incredibly difficult physics challenge over decades. So, construction of the NIF started in 1997. What you're looking at here is a picture of our target chamber. Just so happens it was also the warp core for the Starship Enterprise in the 2013 Star Trek movie Into Darkness. We didn't build the facility for Star Trek. We built the facility, of course, to do fusion. It took us 12 years to complete the facility, and since 2009, we've been doing experiments continuously, so for about 15 years now. During that time, we steadily improved our physics understanding and our computational simulation methods. We built diagnostic instruments capable of taking better, faster, clearer pictures of the experiment. And we consistently pushed up the laser energy and quality. And we found ways to make better targets. And guess what? In December of 2022, we finally did it. Our team at Lawrence Livermore made one of those mini suns on Earth. We demonstrated what's called fusion ignition. For the first time in human history, we ignited a controlled thermonuclear reaction in the lab that was able to generate more energy out than it took to trigger it. That's right, we were able to light the match and turn that into a bonfire, and in the process release a new form of energy that is 1,000,000 times more energetic than chemical reactions. More energy out of the target than the energy put into it. And we've now repeated ignition quite a few more times since. On this slide, I show that we've hit ignition 7 times, but actually we have some new news. Just this past Monday, we had our most successful shot to date, generating over 4 times more energy out than the laser energy that went into it. We've now done it 8 times ignition. All right, exciting times. So, are we done? Well, not quite. To move to a fusion energy future, we now have to harness the energy by building a working fusion power plant. And don't get me wrong, there's still a long scientific and engineering road ahead. Just to build on our success at NIF, we will need more efficient lasers, mass manufacturing of fuel pellets, robotics for automated operations, and more. This is such a big challenge, it's going to take sustained funding from governments and industry and everyone working together. We also know that we rapidly need to build up the workforce that can help us take all these challenges on. And this is where UCSD plays such an integral role. We're all racing to make this future a reality, but there's so much work still to be done. I don't know exactly how long this will all take, but I do know that we can do it. And when we do it, when we make fusion energy a reality, we will make energy so plentiful that it is no longer a limited resource. This will change the world as we know it. When energy becomes essentially limitless, there will be unlimited ways to use that energy. Standards of living, which we know are directly correlated to access to energy and energy usage, standards of living can rise worldwide. Energy will no longer be a strategic commodity that we fight wars over. Imagine that. Energy just becomes a common commodity, as common to us as salt. Each nation will have energy independence and energy security. We can even think of new ways to use that energy to solve our most pressing problems, like enabling carbon capture on a massive scale, which typically is very energy intensive, or desalination of seawater in parts of the world that are clean water scarce. I know, this sounds ambitious and bold. And isn't that exactly what UCSD prepares us to be? To quote Dean Alpisano, together we make bold possible. Now, I often think back on how I got here, how I was so fortunate to be set on this path of bold exploration of one of the greatest scientific and engineering challenges humans have faced. And I have to take a moment to humbly thank my advisor, Professor Farhat Beg. In Professor Beg, I found the most wonderful advisor I could ever ask for. He gave me many opportunities to learn and grow, and selflessly trained me up to be the scientist I am today. In fact, he continues to advise me and support me even today. I just spent half an hour earlier this week complaining to him about some issue I had in the lab. And with so many of the UCSD professors I had the privilege of learning from and now collaborating with, I see the same. caring immensely for their students while furnishing them with the skills and education to lean into the frontier of truly groundbreaking areas of science and technology. UCSD's MAE department is hugely impactful because it integrates and moves seamlessly between both fundamental and applied research. It is curiosity meeting drive to change lives. I stole that from the UCSD website. I thought it was perfect. It was perfect, though. Not only are the students and the staff already top-notch, they push themselves to be even better by fearlessly promoting partnerships across academia, national labs, and industry. This all makes for an incredibly dynamic, responsive, and relevant environment, a guiding star for science and engineering that really makes a difference. Thank you to the MAE department for the excellent training and preparation you gave me. Thank you for illuminating the path for me to where I am now, literally creating my own little stars on Earth. Thank you for igniting the future. Happy 60th birthday, and Fiat Lux.
Okay, so thank you to our keynote speakers for those inspiring and fascinating presentations. Running slightly ahead of time, so in this case, I propose just taking a break for this morning's session. The lunch, I will have to check with Katie, was scheduled for 12, may slightly early, and we reconvene at 1 o'clock for this afternoon's program. So I'd like to thank all the speakers once again, and we'll get to come back at 1 o'clock. In the meantime, there will be lunch. I invite you to stick around and talk to people, ask questions, and have some social interactions. Thank you very much. Okay, so welcome back after lunch to the afternoon session. Thank you for sticking around. I think it's clouded over outside, so much better inside. We now have a number of faculty presentations, 6 of them. I asked our colleagues to tell us a bit about what's coming up in engineering and relate that to MAE, and I hope you'll find it an exciting set of talks. There are 6. They're sort of cross-cutting, and after that we will move to an MAE alumni panel. So our first speaker, Professor James Friend, who will talk to us about biomechanics and medical devices. James, the floor is yours.
Great. Thank you, Stefan. I'm pleased to talk to you and pleased to have all of you here today. It's been an amazing experience. I've worked in a lot of different universities, and I'm proud to call this one home among all of you. A lot of great students. I see some former students came up to me earlier, and I was glad to see them, and also current students are actually in the audience, which makes me a little bit nervous, but glad everyone's here. So let me talk to you a little bit about biomechanics and medical devices, in which we have a vision to use the abilities of mechanical and aerospace engineering in a different direction than the traditional way we normally think about those disciplines. We aim to take the engineering rigor and the skill that is developed as a consequence of all the different problems and things that we've solved in these disciplines and point them towards addressing issues that face us as humanity, and to figure out how the body works and how to overcome issues when the body doesn't work. We combine materials, biology, fabrication, and solid and fluid mechanics with a lot of the different disciplines that are uniquely spread across the different disciplines within our department towards this direction. Our main aim with this activity is really to translate research outcomes to societal benefit, because we immediately have a societal benefit in what it is that we are trying to do here by offering solutions to help humanity. Our foundations are pretty diverse. We have ability to lead research work from complex fluid and biofluid, cellular mechanics and physics, all the way across to medical device design, prototyping, and translation to clinical use. We have David Santillan that works on active matter and fluid structure interactions, and things like bone and soft tissue mechanics by virtue of the fact that Claire Acevedo is in the group. And in fact, this is a point where I think about one of the best slides I'd ever seen was by Claire when she was noting the fact that as we get older, the risk of death is actually greater from a bone fracture than from cancer. And so it made me pay a little more attention to her research work, because she's been working from all the way down from the cellular level up to the bone level. A little bit of work that I do in the sonogenetics and interaction of ultrasound with tissues, with the aim of trying to drive responses from the heart, the brain, the pancreas, for example, in treatment of diabetes, and other organs. Moreover, we do a little bit of work with medical device design and prototyping. As I'll talk a little bit later as well, Padmini Rangamani is one of the leading researchers in the world with regard to cell mechanics and how cell membranes actually interact with chemistry, local and global. Anticipating in the future, we'd see intelligent medical devices. We normally think of things like devices like this, or pacifiers, or whatever. There will be a day when those will be instrumented in such a manner that it'll tell you whether you're actually having a bad day or you're needing to actually talk to your doctor. Already we see some of these sort of things with having like an Apple Watch or Aura rings and these sort of things. But this needs to permeate through the medical profession. For example, the current practice today is for pediatricians to take a newly born baby and stick their finger in the baby's mouth to try to decide whether the baby is actually healthy or not and can suckle efficiently, so that there's no risk of a cessation of breastfeeding. We've shown that, in fact, what happens is that is a little bit worse than even just guessing. And by replacing that process of guessing with a pacifier that is instrumented, pacifier that you would use and actually can buy three in a pack for $8 at Walmart, and put an instrument in it, we're able to measure the vacuum, the suckling of an infant, and then identify with some machine learning how the infant is actually doing. Will they need greater evaluation or not? Will they actually give rise to some suckling issues that could cause a cessation of breastfeeding or not? And the reason it matters is because in the US, 75% of infants actually stop breastfeeding by the age of 6 months. And this has a tremendous adverse impact on the health of these babies and their mothers over the long term. We anticipate a revolution in surgery. Right now, the vast majority of surgical interventions are either open surgery, where they have a large cut, either a large opening in your head or a large cut in your abdomen or other portions of your body to actually deliver some sort of treatment to you. We anticipate the ability to actually replace that, as we see here and there from time to time, via small holes, to use the vascular system and the lymphatic system as essentially highways of the body to go in one location and then navigate to another location and perform functions within the body with small devices that today we can only dream of. It hasn't been all that long ago that most of the tools that our very well-paid surgeons look like something dating from the 14th century, glorified piano wire and knives and other cutting and other instruments. But now what we are talking about is having all these instruments placed at the tip of a catheter to be able to do things like sew, suture, cut, biopsy, and introduce objects all at the tip of a catheter at small scales. And the result of all of this will be that we'll see a reduction in complications and improvement in outcomes for these surgical interventions and a reduction in suffering. That we'll also see an improvement in new treatment opportunities. We anticipate, perhaps some of you have heard of the idea of personalized medicine, but engineering, particularly from the work from our department, has the opportunity to actually make it reality. And two examples of this include the idea of having the ability to detect Alzheimer's early. Currently, the way that Alzheimer's is actually detected is clinical diagnostic. If you remember where your keys are at or not, that's not really a problem. But if you remember or don't what your keys are for, then maybe you need to talk to your doctor. And that's basically the basis for an evaluation of whether you need to talk to your doctor about Alzheimer's or not. But that's far too late. In some early work that we've been involved with in our groups, we've seen in mice that are teenagers, we're able to detect the presence of amyloid beta plaques that indicate the development of Alzheimer's later in life. And the consequence of that is that you're able to actually provide treatment to these animals in this case, but hopefully humans in the future, at a stage where it can make a difference before the disease takes its hold upon you. Moreover, we've heard perhaps in the news about the opportunity to vaccinate against cancer. But the downside is that the process of doing so, where you actually harvest, say, B cells from the immune system, and then train your immune system, the T cells of your immune system, to target, say, a tumor in a given patient, specifically for that patient, by reintroducing those T cells back into the patient, that currently takes weeks at a time, and it's very unsuccessful typically. But we have technologies that have been developed in our department that makes it possible to do this in a single day. So we can go from having a collection of blood from a patient to reintroducing a vaccine for cancer back into that patient in the same day. Anticipate that we'll be able to look at multi-scale modeling and fabrication in biology, all the way down from the subcellular phenomenon to the full body phenomenon. Today, we're only able to produce about 25 cell types of the nearly 200 cell types in the human body. And that's a terrible tragedy because there's a lot of information being presented that suggests that now we're able to produce organs that emulate what the human body has. For example, organoids that represent the brain, the gut, the heart, and other organs of the body. Unfortunately, the actual composition of those organoids pales in comparison to reality. With the ability to generate these other cell types, we'll be able to actually represent better models for these organs and have what we would call, let's say, a human on a chip to provide a method for assessing and answering important questions such as, why do we age? What makes us unique in our responses to disease, say, different from me to you and someone else? How does this drug affect other organs? Maybe you have a new drug that would be fantastic for your heart, but it would not be good for your brain. And these sort of questions we aim to provide the answers to. Out of our particular group, what we're working on as well is delivering people that can work in this entirely new discipline by having the development and implementation of innovative curricula from within the department, but also outside the department, across schools, the School of Medicine and several other schools across the university. And in fact, also with industry. As some of you may not be aware, there is nearly $1 trillion worth of biotech industry in the Southern California area that we're able to be a part of. With over 1,000 biotech firms just in San Diego alone. And all of these firms actually need help. They need people, and we aim to try to help provide that workforce for this new discipline. We have from lead engineers, such as the fellow here, Sean Collingham. He graduated a decade ago from UC San Diego, who's now a lead engineer at producing CGMs, a continuous glucose devices, at Dexcom, all the way over to new faculty leaders. What we're delivering is multidisciplinary graduates skilled in overcoming complexity that's represented by the combining of all these different fields. In this effort, we have strategic partners where we have a unique environment here worldwide. In this UCSD Mesa, within about a 30-minute walk of where you're sitting here today, we have access to over 1,000 biotechs, as mentioned before, big pharma facilities, 5 major hospitals, majority of which actually conduct research activity, and a number of world-class facilities like the Sanford Burnham, the Salk, the Scripps Institute, and the La Jolla Institute just here. Along with that, we have the world-class engineering more broadly, bioengineering and the other departments within the Jacobs School, and the data science, health sciences, the translational research in the School of Management and the Office of Innovation and Commercialization that help partner with us to try to make this discipline grow. What you can see is that actually we have a nice start to a really nice activity. Thank you.
We now have Professor Morimoto, who will talk to us about autonomous and robotic systems.
Great. Yes, my name is Tanya Morimoto. I'm an associate professor here in MAE, and I'm excited to be here as a representative to talk a little bit about some of the work that our groups are doing in autonomous and robotic systems. So to start, I thought I would just show a few images of some robots in the wild. Over the past several decades, there's been a number of advancements that have really enabled the deployment of these types of robotic systems out into the real world. We see just a few examples of robots in the home, for example. We can see a robot vacuum vacuuming up the dirt on the floor. We see examples of robots out in the factories helping with manufacturing and assembly. And we see robots out on the streets in the form of self-driving cars. And we even see them in the hospital in the operating room. Now, despite the large number of advancements, as well as these examples, at least, of these robotic systems, there is still a number of tasks that robots are not able to actually accomplish. And in fact, Science Robotics, one of the premier robotics journals, has actually recently come up with a review article that tried to outline a few of the biggest grand challenges in robotics today. And of course, the field is extremely broad, so this list is by no means exclusive or exhaustive, but they did try to assemble a panel that would try to identify some of the major unsolved challenges. In particular, just to name a few, looking at new materials and fabrication strategies, robotic swarms, and medical robots. And what I really want to focus my talk on today is how we here in the MAE department are working to try to address many of these grand challenges. So here are some of the photos of the group working towards these new autonomous and robotic systems. A lot of us are affiliated with both the Center for Control Systems and Dynamics, as well as with the Contextual Robotics Institute. And our department historically has been very strong in the fundamentals, in particular in control theory and dynamic systems. And more recently, we have started adding to this group researchers working in experiments as well as in applications. And robotics is highly interdisciplinary. We work together with many groups, both within engineering as well as outside of engineering in the School of Medicine and at SIO. And our Contextual Robotics Institute in particular is made up of groups throughout the School of Engineering. And we actually moved, 16 robotics labs moved into our new building in Franklin Antonio Hall in 2022. I think that people will get a chance to tour the labs a little bit later this afternoon. And the really nice thing about this building is that we are actually all housed, all of us from Contextual Robotics Institute, in the third floor of the building in 3 different co-laboratories. So what's really nice is that all of the faculty and the students actually get to sit side by side, and which really facilitates more collaboration. And we are roughly broken out into 3 main groups. We have autonomous systems, cyber-physical systems, and healthcare and medical systems. And while I don't have time to go into what every single research group is doing in the time that I have, my hope is that I can show a few topic areas that many researchers are working on within these areas. So to start, I wanted to talk a little bit about some of the work that groups are doing in planning and control. As the robots that I was mentioning start to be deployed in these complex real-world environments, we see that they are going to have to deal with things that are like obstacles in the environment and other types of uncertainties that are hard to control for. And so because of this, it makes it really important to think about how we can design controllers and planners that can ensure safety in these types of uncertainties. So in particular, there's a few examples here that show, for example, on the left, an example of a robot trying to deal with real-world time delay. And you can see that in this case, if you don't compensate for or predict this sort of time delay, it turns out that the robot can't perform even a simple task. And so we need to come up with ways to actually predict, compensate for, and control these types of robots in these scenarios. And on the right, we can see an example of a robot trying to navigate through an environment filled with obstacles, in this case humans. And you don't know exactly what the humans are going to do. And same thing, we need to be able to have a way to safely plan and navigate through these types of environments. And the groups in this autonomous systems group are in general working on both model-based and learning-based approaches to solving these problems. In addition to trying to control individual robots, we have several groups working to control multi-robot systems. So here, it's important to actually, oh, the videos aren't playing. It's important to actually be able to try to, Okay, it's important to actually be able to try to coordinate the action of these robots to achieve some sort of global task. And in general, these robots can be very useful for things like disaster response and recovery. For example, they could try to provide situational awareness. They could try to suggest paths for emergency responders. They can also be used for things like environmental monitoring. They could help with assessing the impact of pollutants on different biological populations, for example. And some of the main challenges that groups are trying to overcome is how can we actually coordinate these individual robots, and how can we do this while simultaneously guaranteeing safety, predictability, and reliability. In addition, we have several groups working on the challenge of manipulation. So this is going into our cyber-physical systems collaboratory. Manipulation is very important in many applications, including in manufacturing, in assembly, and in agriculture, as you can see from this video here. And this challenge is quite critical, and it's very tricky to figure out how can we design these types of grippers that can accommodate a wide range of objects that might vary in size, in shape, in texture, for example. And these are just a few examples of some approaches shown here. So one example on the right is a bio-inspired approach, and it uses a soft gripper that has a gecko-inspired adhesive to try to maximize the surface contact to enable these better grasps. And on the left, you can see an example of a clever mechanism that uses these tape springs to actually be able to deploy and extend into the environment and can rotate, twist, and actually translate many different objects. And something that a lot of these have in common is that they are taking this approach of using a softer gripper that can try to better conform to the objects and also interact with them in a way that's not going to damage them. In addition, we have several groups working on marine robotics. You can see a few examples here of some work going on with modeling, design, and optimization of these types of robotic systems. You can see a robotic fish being optimized up in the corner, and as well as thinking about how can we actually control these types of robotic systems underwater and in the case where there's very limited sensor information. These robots can be used in general for environmental monitoring, for exploration, and for inspection. And you can see another example of a different type of marine robot that maybe that has to actually try to navigate these really complex environments. So over the sand, into the water, and back onto the sand again. And here they're working a lot towards these better manufacturing approaches that can actually create these robots in a much easier way and that can be much more robust in these types of scenarios. And then finally, getting into our healthcare and medical robotics collaboratory, we're doing a lot of work on these wearable robots. So rather than wearing some type of rigid exoskeleton type robot with these rigid links that might be quite uncomfortable, the idea here is to design these robots that can actually be worn more like clothing. And they can be more comfortable in this way and potentially can be used in the home. So in particular, we are working on these robots for rehabilitation purposes, for helping with maintaining range of motion after a stroke. And the idea is that rather than having to go into the clinic to have physical therapy, you could maybe use this just in your home. And on the right, I see that the video isn't playing, but this is an example of another type of wearable device that we're working on that the idea here is to provide haptic feedback to users. So this could be for things like communication, just like as your smartphone buzzes. It could be used for things like guidance and directional cues, or even to convey social information. And here we're working on more wearable haptic devices that can be more comfortable and that are using different types of actuator technology. And then the last thing for our medical robotics collaboratory is thinking about these more minimally invasive surgical types of robotic systems. So similar to what James talked about before, thinking about trying to make surgeries less invasive and make sure that patients can have faster recovery times. So a lot of the work that we're doing is looking at designing these new types of soft, more flexible, snake-like robots that can more easily navigate through these very constrained, challenging places to reach inside the body. And we work a lot on the design, the control of these systems, as well as thinking about how you can actually steer these at the very small scale. And as you've seen, a lot of this work is very collaborative, both within the School of Engineering, within our department, as well as with the medical school. So overall, I hope that I've been able to show a little bit about how what we're doing here in MAE is really trying to address and tackle these grand challenges laid out by science robotics. We've been working on everything from new material design and fabrication strategies to bio-inspired robots and swarm robots, as well as trying to navigate these complex terrains. We've also been working a lot on new learning methods for robots, as well as robots for medical applications and social interactions. And together, I think that this shows that MAE is really focused on trying to address not just the challenges in robotics, but really trying to have an impact in the broader society as well. And finally, I just want to show that in MAE, we are also trying to bring our robotics research into the classroom. We have a number of examples of hands-on labs in everything from our lower division undergraduate courses like MAE 3, where we have an open-ended robot contest, all the way to our graduate level courses like MAE 204, Introduction to Robotics, as well as Design and Control of Haptic Systems. And we're very committed to both our research as well as to trying to teach and engage the next generation of mechanical engineers. So thank you very much.
Thank you, Tanya. We'll now get to hear from Professor Huang, who will tell us about challenges and new directions in aerospace system. John.
Okay, great. Thank you, Stefan. Good afternoon, everyone. It's an honor to stand here and be a part of this celebration of the 60th anniversary of our department. So I'm thrilled to talk to you about the exciting future of aerospace and tell you a little bit about some of the work we're doing in the department to help bring about and shape that future. So I've structured the bulk of this talk around 5 frontiers in aerospace that each represent distinct classes of future aircraft and spacecraft. The first 3 frontiers are all in commercial aviation, spanning the full spectrum of speed regimes from flying taxis to supersonic transports. The 4th one there is innovations in next generation military aircraft, and finally the space domain. All of these frontiers are enabled by a number of cross-cutting technologies I group into 4 categories. AI and ML are having a pervasive impact across the whole life cycle of aerospace systems, from design, manufacturing to testing, operation, control. Digitization, model-based systems engineering, MBSE, and digital twins are having a major impact. This is all about using virtual representations to do the design and validation for MBSE, and also the real-time simulation and operation for digital twins. Robotics and autonomy, really critical across the board, especially the AAM, the military drones, space domain as well, and finally materials manufacturing is really a critical enabler for all of these frontiers. So now I'm going to deep dive into each of the 5, starting with advanced air mobility. So this is a term coined by NASA, an envisioned ecosystem that of quiet, safe, affordable, short-distance air travel. 2 parts here. So urban air mobility is point-to-point transportation anywhere within urban and suburban areas using electric aircraft capable of vertical takeoff and landing, so eVTOL. Most prominent applications being, as I mentioned, urban flying taxis carrying up to 4 passengers. These are just around the corner, first operation planned in 1 or 2 years, and package delivery and a number of other applications as well. Regional air mobility is likely less well known. This is a vision for scheduled air traffic for city pairs that are separated by maybe a few hundred miles that are underserved because of the demand not justifying conventional airline operations. These enabled by hybrid and envisioned turboelectric aircraft. So with AAM, we have a lot of new novel aircraft configurations where traditional aircraft design methods and sizing methods aren't applicable. So we're doing a lot of research in MAE in high-dimensional simulation-based design optimization funded by NASA. So on the left, you see conceptual. This applied at the concept level using multidisciplinary, comprehensive, multi-operating condition optimizations with respect to hundreds of design variables. And as you can see in the plot here, down in the middle, bottom middle, you can see how these tools can help you visualize how the optimized aircraft weights increase with important requirements like range. On the right, Professor J.S. Chen is leading efforts in structural optimization using advanced computational methods that simplify mesh generation and allow us to do things like rib spar layout optimization. Moving on to sustainable aviation, the focus areas here are unconventional configurations for airliners, so moving away from the 5, 6, 7 decades old tube and wing configuration to achieve breakthroughs in all of these metrics at the top there. And then electrified propulsion, so battery, hybrid, hydrogen electric airliners or airliner concepts are also being looked at. And then for the larger end of the spectrum, turbo electric as well. Sustainable aviation fuels, hydrogen, ammonia-based alternative fuels important for reducing greenhouse gas emissions and pollutants. And at the top right there, the image you see, there's a NASA SFD sponsored X-66 X-plane due to test fly in 2028. Middle right is an EPFD, NASA EPFD program sponsored GE Boeing hybrid electric concept, also aiming to test fly later this decade. So these are really just around the corner. Shifting back to MAE, Professor Abhishek Saha leads a very active experimental combustion research group using really unique world-class experimental facilities to study flame front and thermoacoustic instabilities, really important for understanding how these alternative fuels impacts things. Unsteady turbulent combustion, also droplets and sprays, studying fuel injection strategies and informing new engine design. In my lab, we've been looking at panel methods, which are medium fidelity, I would say aerodynamic analysis method, really a workhorse in the 20th century, late 20th century for aircraft design, modernizing these tools with GPU hardware, data-driven methods and automatic differentiation, and using these to look at optimization of these unconventional airliner concepts. Moving on to high-speed flight, 2 domains here, supersonic and hypersonic. Supersonic transports are trying to make a comeback. The Boom startup with their Overture prototype, they just did their first test flight a couple months ago. The NASA LBFD project is funding Lockheed to develop this another X-plane due to test flight next year. On the hypersonic side, air-launched hypersonic cruise missiles. This has been a bit of an arms race internationally and research momentum is still ongoing there. Secondly, first, using hypersonic powered vehicles as the first of a 2-stage space access vehicle on a longer time horizon. Another exciting kind of future vision is hypersonic transports, being able to fly within 2 hours anywhere on Earth using these hypersonic vehicles. Back in MAE, again, Professor Oliver Schmidt leads a very large and active computational flow physics lab using high-fidelity numerical simulations to better understand jet flows and control jet noise with high-speed military aircraft, and collaborating also with Professor Antonio Sanchez on using these simulations for to understand structure and stability of hypersonic boundary layers. Shifting gears to the military side a little bit more, the 3 main types of vehicles I'd like to highlight that are coming are loyal wingmen stealthy drones. So these are advanced autonomous drones that can operate as an escort alongside a airlifter or air refueler concept, as you see in the middle right there, or as a wingman for an advanced supersonic fighter jet. Attritable drones, this is this concept of developing and deploying large numbers of low-cost drones, and such that they're low cost enough that losses are tolerable, and this is also related to the swarming tactics also being looked at. Research challenges significant in control and design. In MAE, ongoing research efforts, so ongoing and recent, my research group just finished a project funded by DARPA looking at laser-powered drones. So we can really fundamentally change the game if we can have drones that can fly indefinitely through wireless power transfer, either from the ground or from the air with a larger vehicle through RF or laser power beaming. So a very new space here, and again, using these optimization under uncertainty, in this case, methods to understand here how the optimized aircraft mass increases with distance, and you can see above 600 kilometers, this study found that it's not really a feasible design. The aircraft is too heavy. On the right is a new Air Force center. I'm going to talk about this more later, so I'll skip over that. Our 5th and final frontier is space exploration and commercialization. So I'll highlight 3 areas here. Lunar exploration is an important one. The NASA Artemis mission we heard a little bit about in the morning. We're trying to land on the moon again later this decade. The picture on the top right there is of the Lunar Gateway, envisioned Lunar Space Station. Satellite mega constellations and space tourism within this theme of commercialization of space flight, all enabled by significantly reducing launch costs. Key research areas: on-orbit assembly maintenance, space propulsion, astrodynamics, and within MAE, Professor Aaron Rosengren is leading the way there in collaboration with other MAE faculty. On the left, space situational awareness is all about characterizing and tracking objects, debris, natural or artificial, right from low Earth orbit, 100 kilometers altitude, all the way up to geosynchronous 30, 40,000 kilometers. Cislunar in the middle is the region of space between the Earth and the Moon, and doing a lot of work in GNC here to help us get there. We again talked about the lunar exploration topic earlier, using machine learning techniques, nonlinear programming to help with the navigation there and the trajectory design. And finally, space mission analysis is also another important research area. So before we end here, just want to talk about some work we're doing in advanced computational design as a theme that's come up in the 5 frontiers. All of these involve designing and developing new aerospace, new atmospheric and space flight vehicles. And these are entirely new concepts that are not well suited for designing with conventional methods. So a lot of the work I've shown and a lot of the work that we're doing in the MAE department are centered around this vision of an optimization-based design process, where the engineer can choose a configuration, choose a number of rotors, for instance, on this eVTOL UAM air taxi concept, and then the computer can use high-dimensional continuous optimization methods to search the high-dimensional space and figure out the exact details of the shape and so on. So this is this idea of large-scale multidisciplinary design optimization, large-scale MDO, numerical optimization using multidisciplinary models with respect to hundreds of design variables. It's a natural framework to use models to do better design of engineering systems. And it's a theme that has been a focus of 2 large-scale projects that we've been leading at UCSD. In MAE specifically. So the first one is the NASA University Leadership Initiative, very large scale, about $6 million project that we're wrapping up now. Advanced large scale MDO methods and applying these to UAM vehicle design. Professor J.S. Chen and myself, the MAE team members here, along with 9 other actually co-investigators and 7 institutions in total. And we've developed and introduced this new graph-based modeling approach. It's an entirely different way to build computational models to do these sorts of design optimization studies and methods. And this new approach, what it does is it gives us automatic differentiation, which is important for optimizing over high-dimensional spaces, faster execution with just-in-time compilation and GPU acceleration, accelerated uncertainty quantification as well. So we made a lot of advances in this project in large-scale MDO. Just as this large project was ending, we were fortunate to get a grant, a center from the AFRL to apply these methods now to military aircraft design. This team is all MAE faculty, as you see, and we're really taking these deterministic large-scale MDO methods and really advancing them in several directions, bringing in scientific machine learning, data-driven control co-design, optimization under uncertainty, and then applying or incorporating higher fidelity CFD, computational fluid dynamics, and computational solid mechanics tools to do the airframe and aircraft design. So to conclude, I think we have a very exciting future in aerospace ahead of us with all of these exciting concepts coming up, many of them with transformative, not just evolutionary kind of potential. They're all enabled by the convergence of many different technologies that really align well with strengths of our department in fluids, in controls, in optimization, materials, data science. And so our department's really at the forefront of this movement and leading large-scale collaborative projects and addressing high-impact research questions and challenges. Thank you.
All right, thank you very much, John. Our next talk is given by Professor Tynan, who will talk a bit about energy and the environment. This is a very broad topic, and I fully anticipate that he will do justice to it. George.
So thank you for the opportunity to speak today. My name is George Tynan. I'm one of the faculty in MAE. And on behalf of all the colleagues working on the topics of energy and environment, I'm pleased to speak with you today. Just like you've heard in the other talks, the work in these 2 areas in energy and environment is we're really focused on using rather fundamental engineering science approaches to address critical social issues. Things like questions like, how does the ocean exchange heat, carbon dioxide, and pollutants with the atmosphere? What fluid dynamics processes govern those mixing processes, and how do those, say CO2 or heat, transfer between the near surface of the ocean and the deep abyss? That has a profound effect on the Earth's heat balance. Can we power gas turbines with replacement fossil fuels that are sustainably generated? This is things like ammonia or hydrogen. You've heard a bit about that before. How do we integrate very large amounts of time-varying stochastic renewable energy into a high reliability power grid? What's the fastest pathway to a low-cost, high reliability and universally accessible clean energy system? And then the final question, can we make an artificial star, as you heard in Tammy Ma's presentation before lunch? We have a large research effort in those topics. And there are many other questions and topics that we're focused on, but I use these 5 questions to sort of organize the material that I share today. So a number of colleagues are involved in fluid mechanics studies, either experimental or computational or theoretical studies, with an eye towards application in environmental questions. This is work anywhere from, in the lower center, computational work. I think you saw a visualization of this in John's talk. Experimental work on the upper right-hand side, looking at fundamental science of combustion processes. And then there's a lot of field work going on. In the lower left is Gino Pollock's group doing some experiments in the ocean. Computational work goes on in a number of faculty groups. Professor Sarkar is interested in looking at how small scale, that is sort of, foot to maybe 10-foot sort of scale, turbulent mixing processes interact with very large scale flows, and how that then influences the mixing in the ocean. Professor Keiko Nomura is mostly using computational fluid mechanics approaches to look at coherent structure interactions, so vortex-vortex interactions. And in the left-hand side, you see a photograph of several storm systems from the Earth, from Earth orbit, imaged, and then in the middle plot is showing computational simulations of those sort of vortex-vortex coherent structure interactions, and then trying to extract simplified models of the dynamics of these sorts of structures as they interact with each other and with the background turbulent flow field. We have several faculty who have joint appointments between MAE and the Scripps Institution of Oceanography. Xuanting Hao has recently joined us and brings computational fluid dynamics approaches to questions on just understanding fundamental processes in the ocean, understanding how the deployment of renewable energy systems, like say offshore wind, how that affects the environment and the wind flow around a large array of such wind turbines, and so forth. Drew Lucas is another faculty member as a joint appointment between our department and SIO. Unlike the others who are doing mostly computationally focused work, Drew does experimental field work where he develops and deploys novel sensors to measure important quantities in the ocean, salinity, turbidity, and oxygenation, and other quantities. An interesting aspect of his research is, as he tells me, one of the challenges in these sorts of sensor systems is what do you power it with? I mean, you're out in the middle of the ocean, you can't just recharge it rather easily. There's no Tesla charging station nearby. So Drew has developed the techniques to have these autonomous instrumentation systems. As they begin to deplete their power source, they can sort of float up to the surface of the sea and deploy a mechanism to then convert wave energy into electrical energy and recharge a battery. And he calls this the wire walker. And this is a photograph of Drew or one of his students, I'm not sure who, actually deploying this apparatus on a seaborne ship. And that allows much larger and longer duration data gathering from these instruments. And then finally, a number of colleagues, both people who do field work like Gino Pollock and Drew Lucas, and colleagues who are doing more computational work, have joined together on a joint project, a jointly funded project, to look at ocean sensing and modeling and how you can then use that knowledge to improve aquaculture practices. and in this case, growing seaweed as a food in a more sustainable way. So that's just a quick snapshot of the environmental work going on in the department. I'll take a few minutes to pivot and talk about our energy research activities, which are really focused on several different challenges. One, the deployment of large amounts of renewable energy in a high reliability power grid. I'll speak to that in just a moment. We have a large activity in both magnetic and laser fusion research, and then a large activity in combustion research. So let me just give you a few highlights in the time that we have. Renkun Chen is very interested in heat transfer and storage of heat energy, which is if you could store large amounts of heat for long periods of time, this could allow us to have long duration energy storage systems. So he's interested both in the materials development challenges of that, the corrosion aspects of it, and the overall system integration of these types of systems. Several colleagues are involved in computational and experimental studies of renewably generated fuels. There's things like hydrogen or ammonia that could be used to fuel gas turbines, either for aircraft propulsion or for ground-based electricity generation. But when you switch from fossil fuel-based fuels to these new types of fuels, you have to look at the combustion processes in detail and look at the combustion stability and so on, and how that would then be integrated with a device like a gas turbine. So several of our faculty are working on this work. We also have several other colleagues who are focused on the integration challenge of time-varying stochastic renewable generation sources, things like solar PV, solar thermal, and wind, and how one integrates those time-varying technologies with a grid where the demand is varying on a much slower time scale. And in the power grid, you must always match demand and supply to a very, very tight tolerance. Otherwise, the voltage and frequency of the grid becomes unstable. And so we have several groups who are exploring how to do that. Carlos Coimbra is very interested in looking at the question, if we deploy renewables on the requisite scale to make a significant difference in carbon emissions, that means you're going to then deploy literally thousands of square kilometers of solar or wind turbines and so on. So the question then becomes, what effect does that human-built system have on the environment? And so Coimbra is exploring those questions today. And then finally, Michael Davidson is a colleague in our department and then has a joint appointment in the Global Policy School. And Michael is interested in looking at what happens when we deploy renewables on the requisite scale, and what effect does that have on land use, and how do you integrate those resources with the either existing or with a feasible transmission network. So in this case, his work is focused on China. And I'm not sure what happened. This has some animation. I forgot about that. And then finally, Professor Patricia Hidalgo Gonzalez is looking at more locally at California and the US, how do we control a grid that has a high fraction of renewable power generation in it. Let me then pivot to some of the work we're doing in fusion. In my own lab, if I were to try to describe it to you, we're trying to answer the question, if you're trying to hold a star in a jar, what do you make the walls out of? And so we have an experimental facility in the basement of EBU2 that'll be on the tour today that we're using to try to study in a controlled way how different materials interact with the fusion plasma. We have a strong effort in fusion theory. Sergei Kreshnenikov has made profound and fundamental contributions to our understanding of how heat and mass gets out of the hot plasma. How can we quench the hot plasma before it hits the wall and damages the wall? That's called plasma detachment. And in this case, Sergei made some fundamental contributions to our understanding of how particle and heat transport occurs in the last few centimeters of the hot fusion plasma. And then finally, we're home through the leadership of Farhat Beg with a Center of Excellence on matter under extreme conditions. This is matter in the conditions like the experiments that Tammy Ma described this morning in laser fusion, as well as in other applications in national defense and so on. Finally, You saw the famous equation E equals mc squared in Tammy's talk this morning. And usually we see that in the context of we're taking a little bit of missing mass from the nuclear reactions and it's been converted into energy. Our colleague Alexei Arefiev is so taking it the other way. He works on the most extreme, intense laser pulses that exist on the planet today. We have two, he's showing the lower left-hand side, two laser beams have interacted with the plasma. They're so bright that the plasma then generates gamma rays, which are very, very intense photons. And then the beams of gamma rays are sort of colliding with each other. And in this case, the gamma ray intensity is so large that some of the photon energy is converted into mass. So you're going the other way. You're taking energy and turning it into matter. In this case, electrons and positrons, matter and antimatter. And where that goes, who knows? But I think it's really cool. These experiments can generate magnetic fields that are a gigagauss. The Earth's magnetic field is half of a Gauss. So this is 1 billion times more intense magnetic field than the Earth has. So anyway, I think this is fascinating work, and who knows what it will lead to. So in wrapping up, almost half the faculty in the department are working in these sort of topical areas, and we're trying to address critical questions that address problems that we need to solve. And we're using the fundamental approaches to do so. And with that, I'll show a quick picture of all the folks who are involved in this work, and thank you for your time and attention.
Thank you very much, George. Perfect timing. Did the subject justice. Our next speaker will be Professor Poulikakos telling us about the future of materials. Lisa.
Hello, everyone. My name is Lisa Poulikakos. I'm an assistant professor in the MAE department, and I'm really delighted to have the opportunity to speak with you today about our work and vision on materials for the future at the MAE department. So if we think about the importance of material science and engineering for the progress of humanity, it's really profound. If we go through the ages, starting from the Stone Age to today's Silicon Age, we really see that these ages are named by the materials that humans had mastered at the time. It really shows how important materials are for the progress of technology and humanity. But the question I'd like to discuss with you today is, how can we achieve the next generation of materials? So in order to do that, we need to understand the properties of materials and manipulate them for new applications. These can be electromagnetic, thermal, mechanical, acoustic, chemical, or optical. So in our department, we like to follow this path from different perspectives. The first approach is to put these materials in extreme environments and develop and tailor them accordingly for different new generations of technologies. These extreme environments can be extreme laser power, heat, pressure, or chemical exposure. The other approach we like to take is to develop so-called metamaterials. These are designer materials that can surpass what is possible with materials found in nature. So just like natural solids that are arranged from periodic assemblies of natural atoms, metamaterials are designed from periodic assemblies of designer meta-atoms that we can engineer in ways to respond specifically to different stimuli. So these are our two branches of materials research today, where I'd like to highlight some of our work in these areas to you. I'd also like to note that we're a part of a very strong cross-departmental materials science and engineering program, the MATS program. This program was started in the 1990s and continues to thrive today. It's a university-wide program with around 100 faculty and around 200 students. It's led by our wonderful MAE faculty member, Professor Olivia Greve. You can see here that we have some really interesting thrust areas for the students to learn from that are quite future-oriented. So I'm delighted to give this presentation today, but this is really a team effort, and I'd like to also acknowledge the wonderful faculty in our department who are doing pioneering work in materials science and engineering. So first, I'd like to highlight some exciting research happening in our department on materials in extreme environments. First, Professor Olivia Greve's Extreme Materials Lab is revolutionizing the way that we design, test, and manufacture materials for extreme environments. This can have important applications in aerospace, nuclear engineering, environmental as well. And she's also the director of the Kalibaja Center for Resilient Materials and Systems, which allows us to push these ideas further even more. Professor Vitaly Nestrenko has done some really pioneering work on developing novel materials for high pressure and high temperature processing. These include magnesium bromide, bulk materials or coils developed from powders, or ballistic grade titanium alloys that they've tested for all kinds of important material properties, including superconducting even, or micro hardness. Professor Mark Myers is working with the National Ignition Facility, which we heard all about in Dr. Ma's inspiring plenary talk today at Lawrence Livermore National Laboratory. You can see another image of the very impressive facility here, where 192 high-power laser beams enter the chamber. The resulting fusion reaction allows to large amounts of energy to be released, and the Myers group is leveraging that to understand dislocations in diamond materials under extreme loading. Professor Javier Garay's lab has done some pioneering work on new materials for fusion reactors that can really withstand these extreme conditions of fusion, such as temperatures, pressures, and radiation. And they've also spearheaded some really exciting work on ultra-fast laser welding of ceramics, which has many important technological applications. Professor Renkun Chen's lab has done a lot of really exciting work on thermal energy materials and materials physics. One exciting application is shown here, where they've developed materials for personal cooling. So these are thermoelectric materials that a wearer can simply put on to experience cooling in extreme heat environments. Professor Claire Acevedo's skeletal tissues lab is doing some really exciting work studying how bones break and how bone fragility can be related to diseases from the cellular to the macro scale. So they like to place their bone samples in extreme environments, for instance, extreme chemical exposure to understand how diabetes works, or extreme temperatures to understand protein denaturation, to better understand the origin and propagation of disease based on the material properties. And Professor Sheng-Hyun Kai develops advanced polymeric materials for all kinds of exciting applications. One example is shown here, where they took some of these beautiful bioluminescent algae from the ocean and embedded them in polymer matrices. Then they were able to develop mechanoluminescent living materials that light up or fluoresce depending on their mechanical stimuli. So after sharing some of our extreme environment materials work from the department, I'd like to talk to you about some of our research on metamaterials. So first, I'd like to share a brief history of metamaterials at UCSD. Metamaterials, unlike natural materials, are composed of periodic arrangements of artificial meta-atoms that are specifically engineered to respond to different stimuli. So the first experimental demonstration of a metamaterial actually happened at UCSD, as you can see in the publication highlighted here in the physics department, but also in collaboration with our MAE faculty member, Professor Nemat Nasser. So what this paper showed was the first experimental demonstration of so-called negative refraction. So most natural materials, when they interact with light or an electromagnetic wave, experience positive refraction. So you can see here this glass with a straw inside, the light kind of refracts in a way that we're used to seeing. What the metamaterial was able to do, which does not exist in nature, is refract the light in a negative way, bending the light in a direction that a natural material cannot achieve. So the demonstration of metamaterials was really allowed the field to explode and blossom worldwide. It's a very active research area, and metamaterials are currently being studied across disciplines, ranging from acoustic to thermal, photonic, mechanical, robotic, or biological metamaterials. And in our department, we're touching upon all of these research branches, and I'd like to talk to you about some of the highlights of some of the work we're doing today. Professor Michael Fraser's lab is doing some really exciting work on phase transforming metamaterials. So in these systems, he manipulates the structural hierarchy and tunable defects by looking at different phases. And with that, he's able to create interesting patterns in the structural behavior, as you can see here in this beautiful bumblebee design that his systems were able to generate. Professor Prabandru has done some really exciting work on metamaterials and pushing the boundaries of materials physics from a mechanical engineering point of view. So here, for instance, are some examples of his work on looking at metamaterials for fluidics. Here you have an example of a liquid-filled superhydrophobic system, which allows the flow to generate voltage. He also developed many thermal metamaterials, which are able to focus and redirect and bend the heat flux in ways that isn't possible with natural materials. Professor Hailuan Lan has done some great work in the realm of robotic metamaterials, where some of his systems include skin interface sensors and actuators that can augment human sensation, as well as responsive systems he's developed that interact with biomaterials and biosystems. And Professor Nick Beckler has done some really exciting work on developing new materials with new kinds of mechanical and dynamic properties. So one example shown here is that of unconventional elasticity, where they developed a metamaterial that can propagate elastic waves unidirectionally without any backscattering. They've also done some really exciting studies on natural materials, where, for instance, here you can see their studies on onion cell scaffolds, which are able to propagate elastic waves in really interesting phononic crystal ways. And finally, I'd like to share some work from my own research group. In my lab, we study optical metamaterials, so materials that are designed to interact with light in new and interesting ways for next-generation imaging and diagnostic applications. The first example I'd like to highlight is a collaboration with Professor Beckler's lab, where here we developed a new class of acoustoplasmonic metasurfaces. These are materials which have the ability to transduce and convert light to sound. So we can send in an incoming laser pulse and generate a patterned acoustic wavefront with any pattern we like. For many versatile applications. So as a proof of concept demonstration, we showed some school spirit and generated the Morse code of UCSD with an acoustic wave, as you can see here. By switching the polarization of the incoming light, the Morse code will switch from either UC to SD. Another project I'd like to highlight from my lab leverages the beautiful morpho butterfly wing as a natural metasurface based on its micro and nanostructured surfaces here. And we leverage this butterfly wing as a new tool to diagnose serious diseases such as Alzheimer's disease, heart disease, and cancer in a quantitative, label, and contact-free manner. So as an example disease, we looked at breast cancer tissues, as you can see here, and we interfaced them with the morpho butterfly wing. So based on the optical metamaterial properties of the butterfly wing, it's able to selectively enhance important disease signatures in the tissue. As you can see here, on the bottom row, we have our tissue interfaced with the morpho butterfly wing. The signal is strongly enhanced so we can understand properties of the disease that are currently very difficult to establish in the clinic. So this brings me back to our first question. After thinking about some of the exciting materials advancements in our department, how can we achieve the next generation of materials beyond the silicon age? And we're really excited to think about the future as a metamaterial age, where humans can leverage our deep understanding of materials properties and physics to design and create designer metamaterials which push the boundaries toward specific, tailored, and future-oriented applications. And we're really excited to leverage the key expertise and deep knowledge in the MAE department studying materials in extreme environments. And we really envision exciting future research directions where we can create metamaterials that are specifically designed for extreme environments and new frontiers and technologies. With that, I'd like to thank all of my wonderful colleagues who are really pushing the frontiers of material science and engineering in the MAE department, and thank you for your attention.
Okay, thank you very much, Lisa. Our last presentation is given by Professor Shea, and she'll talk about engineering education and the future. Over to you, Hui Hui.
Good afternoon, everyone. I am Hui Hui Qi, an associate teaching professor at MAE. It's my honor to be here today to celebrate MAE 60th anniversary with everyone. So the convergence of research and education really creates a positive cycle for knowledge generation, application, and advancement. My colleagues have given research presentations conducted here at MAE. Next, it's going to be my pleasure to present about the educational programs. I'm sure the audience today here has been very familiar with the prestigious ranking we have kept over the years. But today, my presentation is not focused just the outcomes, but more about the approach and the process, what we strive for to give the students the best educational experience at MAE with examples. At MAE, our educational goals are to educate future technological leaders. Our students after graduation is going to have diverse career paths. They will work for different industries in different sectors. And our goal is to provide them the skills, knowledge, and mindset to be successful in any career path they will pursue. We emphasize on strong technical foundation with critical thinking and problem-solving skills. Also, professional skills so they can work effectively in a multifunctional team. Lifelong learning skills so they can be always at the frontier to use newest technology and knowledge. We also develop their leadership, vision, and impact-oriented mindset so they can think big, think forward to make a positive contribution to society development and human advancement. To achieve this goal, we use a holistic and resilient approach. We have a rigorous curriculum, provide students diverse core curriculum opportunities. We integrate cutting-edge technology, use evidence-based, student-centered, innovative pedagogy to support diverse students' body, bring their own agency to their own education, empower them to be prepared, solve tomorrow's problem. And our approach is collaborative between students and faculty, faculty and faculty, MAE discipline, and other disciplines, and also academic with industry. Our curriculum emphasizes the importance of both fundamental knowledge and experiential learning. In our learning process, we train the students always use fundamental concept to make informed engineering design decisions. And also give them the opportunity to develop a range of additional skills such as teamwork, communication, to understand the difference, also to understand the difference between theoretical result and practical result. Also, we take advantage cognitive science learning principles, give students the opportunity to take advantage embodied cognition through hands-on learning to better understand fundamental concepts. So they deep learn the concept instead of surface learning. Our degree specialization brings students agency into their own education, builds their confidence and identity being an engineer, and develop their expertise for the path they are passionate about. Throughout their time at MAE, our students grow their knowledge and skills constantly. We challenge our students with high support. For example, let me play this video. For example, many of our senior design projects are sponsored by real-world projects, and they're challenging. Although our senior design instructors are 6-6 official instructors, all of our ME faculty are here to support our students, provide consultation whenever they have a problem aligned with our faculty expertise. And our pedagogy are truly student-centered, learning science-grounded, and evidence-based. In other words, we teach based on how human and our students best learn STEM. And our faculty are always thinking about how to innovate in teaching, create tools, instructional materials, and new methods to engage our students, increase their motivation, and enhance their learning outcomes. We also collect data and analyze the impact of our teaching innovation to continuously improve for the future. Our dedication and innovation in teaching not only benefit our own students, but also advance the research field of STEM education. Our faculty has been conducting pedagogical research at MAE. They have been bringing external funding and internal funding to support educational innovation, including some NSF grants. And more than 25% of our faculty have published pedagogical papers, over 70 in the last 5 years alone. The topic ranges anywhere from how to support students best learn conceptual knowledge, to increase their intrinsic motivation or grow them as lifelong learners. And we're making positive impact through our educational innovation in society. Our educational innovation has been highlighted in many media stream. For example, the recent oral exam project has been highlighted in Wall Street Journal that attracted many educators from the other discipline and other university to adopt similar approaches to benefit their students. We also provide a range of co-curriculum opportunities to support our students' diverse interests. From being a research assistant in our prestigious research lab to students' clubs and organization, or being an instructional assistant in a classroom, every student can find their own opportunity. Our innovation in education is always dynamically adaptive at the programs level, in the classroom level, and our students level. For example, a recent educational innovation project for 2 years, we updated our lab and design class to enhance students' experiential learning. In this project, we bring in the newest technology and equipment, enhance students' learning, and bring them the most cutting-edge knowledge. We also transform some of the traditionally lecture-based classes into hands-on classes to further enhance students' learning. The dynamic adaptive feature builds our resilience. So our educational program is always ready to address any challenges we face. During COVID, we successfully and quickly adapt to remote learning and make sure our students has been always fully engaged, highly engaged. Our faculty use innovative assessment approach to uphold rigor and academic integrity, engage students in deep learning. Those successes are not just for lecture-based classes, but also those hands-on learning and lab classes. For example, our MAE 3 professors and teaching assistants developed and built hands-on learning kits, shipped them to students all over the US and several countries, so they can still achieve the same hands-on learning and experiential learning goals, even they were at home. This success has been achieved in all classes. Another example is our senior design classes. Our students not only was able to finish their own project, complete their degree at home. In fact, the product they developed through their senior design were able to support UCSD Medical Center so they can continue their medical training. The examples I have been given are mostly from undergraduate program. However, we use the same approach in our graduate education so students get similar, rigorous, and diverse learning opportunities. Education is always evolving, along with society and technology advancement. And today, we are in the age of AI. And MAE is at the frontier actively examining how AI is going to impact education in terms of what do we teach and how do we teach. Needless to say, the role of critical thinking and solid foundation knowledge in metacognition become even more important today with AI tools available. So we want students to be able to know the limitation of AI tools and make sense of the result from AI tools. And also, we want to teach our students AI literacy in the context of engineering problem solving so they are ready for their future. We also hope to use AI educational tools to enhance our students' learning and learning experience. At the end, I want to say, high-quality education is truly a teamwork. I cannot express how important this teamwork is between faculty, staff, and our teaching assistant. I know you may actually wonder, why do I use gears to illustrate teamwork? Because we are in MAE. Of course, we cannot emphasize more our letter-ranked faculty, how their prestigious research, and passion for education plays such an important role in our education programs. We also have many other faculty take significant leadership and responsibility for MAE education. We have 8 MAE teaching faculty who teach many classes and lead educational initiatives. And they also serve as catalysts for many educational innovation. Our lecturers and professor of practice teach many classes as well. And also, finally, I want to have a big shout out for our educational staff and student academic affairs staff. They directly involved in our educational activities for their service, advising our students to navigate their academic career. If the saying, a person's home zip code is important for their future, we are working hard, strive to make MAE this zip code, 92093-0411, to be our students' forever home. This is a home students explore, develop their knowledge safely, fully develop their full potential, and make lifelong friends and start their bright future. This is a place, the home. We are always proud of our students and alumni, and a place they would always be proud of. Finally, I want to say, MAE alumni, welcome back home. Thank you.
Thank you, Hui Hui. I'd like to thank all the speakers, in particular for a chance to survey the entire research mission of MAE, to think about the future, to think about our teaching programs, and to think about the department as a whole. The next item on the agenda is an alumni panel. It'll take us a few minutes to get everyone sat down and set up, so don't go away. In a few minutes, we'll start the question and answer session. So let me thank once again all our speakers from the session that just finished. Okay, I think we're going to reconvene. If we could settle down. Let's give our panel speakers some quiet so they can hear themselves think. So welcome to the last session of the program in the auditorium. We're now going to have a panel of distinguished alums, and I have some questions to ask them and to hear a bit about their thoughts. As we start, maybe the first thing I can do is just to go down the line and have you briefly introduce yourselves, your link with MAE and what you're doing now, and maybe we'll start just going down that way. Sure. Rachel.
Sounds good. Hi, everyone. My name is Rachel Flanagan. I graduated from UC San Diego Department of MAE 2021 with a PhD. I work at Northrop Grumman, and I'm a manager of systems engineering and do some really fun stuff with ground comms.
Thank you, Rachel.
Neil Bloom. I graduated mechanical undergrad here back in 2008 and worked in aerospace for a while, and then started a few software companies, and have built and sold a few software companies, then got into the early stage investment world, first as an angel, and now have my own venture capital fund investing in early stage hardware and software.
Thank you, Neil.
Wayne Dunstan. I graduated with my PhD in aerospace engineering in 2004. Seems a long time ago. And I work at a company called Cymer, which is part of a bigger company called ASML. And I head up engineering for our deep ultraviolet light sources, which are used to make silicon chips.
Hello, good afternoon, everyone. My name is Jocelyn Lowe. Graduated from Ames back in the days, 2002. So it's been great to be back and see familiar faces and professors. Thank you, from 20 years ago. It's amazing here. I have my own consulting company now. Graduated from mechanical engineering, mostly focused on engineering program management. Good to see you all.
Thank you,
Thank you. Good afternoon, everybody. My name is GB Singh, and I did my MS and PhD here 2021 when I finished my PhD. It took me 9 years to get it done because I do work at solar turbines, and I continue to pursue my PhD. So very thankful to UCSD. Actually, it's great to see my advisor right there, Miroslav. Thanks for being here. It's an honor to be here, and I'm so excited to be a part of this panel. Thank you.
Okay, great. So thank you very much. So I have some questions. They were shared with the panel, so there should be no big surprises. And I thought I'd start with a question about the undergraduate experience, and so maybe we can pick out Neil and Jocelyn, who are undergraduates. So maybe you can start with Jocelyn. So tell us about your undergraduate experience studying in Ames at UC San Diego, then experiences you'd like to share with us.
Yeah, I think everyone knows UCSD has a really great MAE program, so I don't have to go into that. But one thing that I remember fondly, it's although there's a lot of stress and classwork, a lot of busy schedule, I took a area of focus in dance, so I took a lot of dance classes to kind of help me de-stress, which I still take to this day. I still go to, the aerobics, the yoga, to balance out my, tough work life. So that's something that I took still with me, to be able to have a healthy lifestyle, even though you have a lot of coursework that you need to address and homework and tests and stuff. But no, that's one big thing for me.
Good idea. Neil, would you like to comment on?
Sure. Yeah, for me, I got heavily involved in the project and clubs of the Jacobs School of Engineering, pretty much rebirth ASME. And for me, I wanted to use it as a platform to connect students to undergraduates to engineers. And so we did a monthly tour every month to go see, Cymer and Northrop and a bunch of offices of what is it like to be an engineer professionally. And so I got very involved in that. And as well as starting some clubs. Went from the human-powered submarine team, which I loved, and then we started the UAV team and built kind of the first cross-functional club that included just as much computer science, electrical, mechanical, and aerospace to compete at, I think it was an Army competition. And UCC was year one, and we won like best paper, which was kind of fun to have an autonomous plane, but also, represent on the East Coast. So that was a fond memory for us, for sure.
Thank you, Neil. Neil brings up the important point of student clubs, and Jocelyn in general, important part of student life to do many, many things. During after this session, there'll be some lab tours, but also there'll be a chance for some displays from some student organizations. So I hope they'll show some of their latest toys, and well, not toys, very serious, very serious devices. Okay, so I'm now going to turn to the panel members who did graduate study here. And so my question, I'll start with Rachel, so she's on this side, is how was your graduate experience studying at UC San Diego in MAE, and any experiences that stood out for you?
Well, I had a phenomenal experience. I always tell everyone UCSD is definitely an amazing place to be a graduate student. Educationally, amazing. I thought the previous talk about oral examinations was pretty interesting because I actually loved the oral exam process, which is probably weird, but I thrived. It was the first time I took a test and thought I did great. So that stuck with me. I feel like it builds up a lot of resilience, and I understand the power of not knowing and telling people you don't know something so that you can kind of peel back the layers and actually figure out something new and innovative. I also resonate very much with student life. I was a part of the club field hockey team. We won a championship when I was here. And then I also got to be a part of student government. So I was student body president of the GPSA, and I think one of the biggest things that I carry with me dear to my heart is I also worked with the department women's group, and we kind of reinvigorated that. I don't see the professor who supported that and mentored me there, but we actually started a mentorship program. In the first year we did it, we had like 40 people between grads and undergrads engaged, and then when I kind of handed over the reins, we had like the kickoff event had like 120 people. So I carry that memory really fondly in my heart of how much community we're able to grow through that program. So yeah.
That's awesome.
Thank you, Rachel. Wayne, what do you have to say on that?
Well, this was 20 years ago, so we'll
Just
say
like yesterday.
It seems like yesterday. We'll say the memories I have are of the academic rigor, definitely the coursework. I was very impressed, whether it was nonlinear controls with Miroslav or nonlinear system identification with Bob Bitmeat. It was very high strength academic work. I think working with the students, I was part of the Graduate Student Association, and I brought back the barbecues at School of Engineering. Then we extended those to happy hours with Scripps Institute of Oceanography because they had a better view out to the ocean. So, and then I guess finally is incorporating industry in with my PhD. I think UCSD has a lot of fantastic partners in industry, and I was able to do internships and continue my research in industry, which I thoroughly loved. So,
thank you, Wayne. GB, tell us about your graduate experience at UC San Diego.
Yeah, Stefan, when I think of any university, I would say anybody can build a university with brick and mortar. It's probably easy to do. But what really where UCSD stands out in my mind is the soul of any school, which is the faculty. The faculty that UCSD has. So I'll speak to my personal experience. I did my PhD in controls engineering, and they were the ones I worked with. Of course, I knew by looking at, I want to pursue controls here because they were top notch, right? They were well funded, they were very well known. We spoke about Miroslav, Bitmead, Raymond, you name them, they are well known worldwide. But I think what is very unique about all these faculty is that how easy it is for a student to approach them and how invested they are. I was a working professional, I can tell you that they were invested in my career. They helped me, they pushed me actually that GB, complete this will help you. They gave me options to, attend classes remotely. They allowed me to, do a lot of things. There was utmost flexibility provided because they want to see student success. And I'm an example of how a faculty can be gets invested in students' future and make them successful. And those are the most cherished memory for me on the faculty involvement in my success.
Great, thank you. Any other comments on that question from the panel? No?
Actually, I just want to tell you that the barbecues and the socials live on. GSA is now grad and professional student association. We're inclusive. But we get the med school money now.
Yes.
Okay, good. All right, so those are sort of questions directly about your time as students at UCSD. And we have a question now about, were there any surprises, things that you learned that were of value to you later in your career? So at this point, feel free to jump in, or I will pick someone, which students hate when I do that in class. But anyone want to talk about surprises from when they were here that turned out to be relevant later in their career?
Yeah, I guess I can speak
Go
up
ahead.
just real quick. Something that I didn't know that was helpful was actually presentations in the senior project. We had weekly presentations, and at that time it was just a homework, but I didn't know that actually grew me to be comfortable in public speaking, to present projects, and to collect all the data that our team have done a phenomenal job in collecting, but to digest it and present it. And that skill, I didn't know that it was important, but turns out it's very important. I think I can speak for ourselves, like all of our careers. It's one thing that you can truly do the work, and then is another to actually present it in an orderly manner. So that was actually a surprise for me, but I think maybe UCSD faculty knew that is something that we all need to learn. So that was a big bonus.
That's a good one.
Okay.
Yeah, if I may add something similar to that, one of the skill that I did not realize the power of it is the collaboration and the interdisciplinary if you would say collaborators that can come together. I really feel that was something I learned as part of my MS PhD journey at UCSD, was how these different disciplines of engineering, actually beyond engineering, they all come together. And how you can, pick from the abstract from each of those disciplines and create something very unique, which you can take to the market. So I think that journey of leveraging those abstracts, creating a unison of all of them and bringing that to a real life product or service is something that was dramatic learning for me, and which actually I took it back to my company, Solar Turbines, and I used to head the R&D division there, and we developed some cutting edge products just based on that learning, and which is we are reaping great rewards of that. So phenomenal learning, and something that I could easily apply into my work life.
Thank you. Any other comments from the panel?
Yeah, I'd say for me, a lot of the labs were, felt introductory of like, here's a thermocouple, here's how it works. And I can't tell you how many times having knowledge of what a thermocouple does and works just gives me the ability to just start something in most of my aerospace career, where whether it was working on kind of the R&D center for the Bradley fighting vehicle up in the Bay Area. And my summer project was create a air conditioning unit because they didn't have one. It was designed 30 years ago. In Iraq, it gets 155 degrees inside and no AC. And so the value of knowing how to, one, just take sensors off the shelf, plug it in, build an air conditioning unit, which pretty much just had to find a welder to sit alongside me, do the system, and wire it up and say, yep, it's 65 degrees, it works, thumbs up. And so just kind of the value of just like, that just came from a lab, from being, introductory to lab science. And that has stuck with me, the value of sensors and the value of measuring things to have a feedback loop to know that things are working or they're not, and course correct. So that's always been stuck with me.
Amazingly enough, Neil has not been paid to say that by Nate or the control room. Any other comments on that? Maybe I'll pick on Rachel. Rachel has the unfortunate disadvantage that she did an interview and I was able to hear her talk. And one thing that you said, Rachel, was about, I'll come back to what you said before, about being able to know when you don't know in an oral exam. So can you kind of clarify this a bit? What did you learn from that you were able to use in your career?
Oh man, I use that all the time because I think, so I lead like multiple teams of like a couple dozen engineers, and there's no way that I have the depth of knowledge in all their fields to probe into what they're doing or to replicate what they're doing. But being unafraid to go in and say, I actually don't understand what you're saying to me and I need you to break it down again, actually helps me a ton, because I look at like big systems now and integrating a lot of parts. I've got mechanical, I've got mostly electronics engineers and network engineers, and kind of being able to put things together, and for me to tell my engineers, I'm not sure what that means. They empower me with information, because otherwise I have to go tell my leadership, I don't know what that means. And then you have to take that hard punch that you take in the oral exam, which I'm not afraid of. It translates to my career really nicely, but I try to avoid it. So I try to say, I don't know, to the engineers before I do the management. But yeah, that was a huge benefit of going through the rigorous process here for the PhD. I feel very comfortable under pressure, and in those kind of, if I don't know something, I'm not gonna tell you I do.
That's why we picked you to be on this panel, comfortable under pressure. That's right. Any other comments on that question?
I'll just add one thing.
Please.
I didn't realize till I did my PhD how important linear algebra can be in life. So that was a big learning for me, and everybody in my household knows what an eigenvector is. So that was
of course.
It was a big learning for everybody.
That's deep learning. Okay, next question. And I think we're moving on a little bit from your career to the interactions with the department. So the question here, which is, what has been a rewarding way that you've engaged with the Department of MAE, and what inspired you to get involved? So anyone want to, I know that Rachel and GB are involved, but maybe anyone wants to reply to that? You've gone all quiet.
So when I
I
started here, I got a group of us to go volunteer at the Price High School's first robotics team, which was really rewarding because it's what got me into engineering in high school. And then I left and continued volunteering, but saw that continued on, which was really cool to see that MAE undergraduates and graduates just walking over and helping students. So that I've stayed in touch and made sure that linkage keeps happening in that regard. I've stayed in touch with Professor Delson from time to time to understand that. And funny enough, last week was in some new hardware shop over in Bar Logan and saw the exact same laser cam that we had, 20 years ago. I was like, wow, that actually does get used in this industry. That's good to know. And so, seeing professors go into industry and then go back. One of my professors, Professor Buckley, and I reconnected very recently. We actually share deal flow now, investment deal flow, even including some students that he's mentored and advised over time. And so, yeah, it's kind of fluid, but I'd say just the ability to know a point of contact that you had a relationship, check in on them, see where you can be helpful and help each other, and then networks just move. Some people move off campus and move back on. That's been really fulfilling to have that network and support system that started all at ME.
Thank you.
Very cool. Maybe a quick one that I believe staying close with the department, to students, to the professors, both in research opportunities, internship opportunities. We've hired quite a number of students from MAE and at our company, and so I like that full cycle of engaging students when they're in their degree, PhD, masters, and following them through their education in MAE, and then potentially coming into the company. It's a really great thing to see.
Thank you.
I guess another perspective is I was more involved in the Career Services Center. I had a few webinar during COVID times about tips on interviewing and stuff like that, and it was really fun. And actually did a few in-person kind of seminar as well, and was able to actually grab a few drinks with coffee with the students on campus to chat, and it was actually quite an eye-opener, because I remember when I was a student, I didn't reach out enough to actually have someone in the industry to tell me how it's like to be an engineer or a program manager. So it was a really fun experience for me to share that, give back to MAE Department and UCSC in general.
Maybe I can briefly add, I think GB wants to chip in, but one of my goals as chair here is to make sure that we have contacts with alums so that the students and the faculty, everyone is in a position to engage in a way that is most helpful. I think there's many, many wonderful connections to be made between alums, faculty, and current students. I'm sorry, go ahead, GB. I think you were starting to say something.
For me, any alum who always wants to connect back, I always say it's a personal relationship. You know, it's something very personal, something you hold very dear to your heart. You know, I, as a student, when I came to this country, I was always attracted by the entrepreneurial spirit and innovative spirit of US. And this country, I had very humble beginnings. This country, UCSD, MAE, gave me everything that I am today. So for me, this is my way of paying back to our school and say, hey, thank you. This is the least I can do. And I always want to be that champion for UCSD in the industry out there to make sure that I can, wave their flag. But again, it is something very personal to me. And I believe that, it is an onus on the industry that they need to make sure that they are building those bridges with the academia and companies like mine or Qualcomm, or for that matter, Cymer. I think the onus is on industry to make sure that we can feed back that loop into the academia to make sure that they remain relevant and they produce the best product that can be leveraged by the industry.
Thank you. I think we may come back to that in a minute. Has everyone had a chance to answer that question? Rachel?
I mean, I'll just say I think community is everything. I think I can look at the numerical measures of success for me, and I see where I had community and where I didn't. And I also see where I had good mentorship and I didn't. And so coming to campus for me, I think I'm here at least once a quarter. And it means a lot for me to be able to see kind of what the next innovations are, because I intend to kind of grow those from my professional perspective, but from a personal, just pay it forward, give it back, make sure that the students are kind of see what the pathways are. There's from time to time, folks will connect me with students who are looking for just a resume review, or there's a student who was just inquiring about career pathways, and taking a little time to kind of foster those relationships is kind of my way of leaving the door open, because when I was a young person, man, I didn't know many people like me, but my goal is for kind of the students to see how many of us, kind of successful graduates of these types of programs are out there, and all the different directions you can go.
Thank you. So maybe one thing I can briefly remark is that a number of the panelists have or are serving on the MA Industry Advisory Board, which is a board that advises us, and particularly important in terms of accreditation. We need to have feedback from industry, and I thank them for their service. And Neil and Jocelyn have been involved in a number of ways. Leslie, who is around the development, makes sure we try to engage with alums in all kinds of ways. So if you as alums are interested in being involved in the department, please do not hesitate to reach out to me or to Leslie. We're very happy to talk to alums, because there's many wonderful things you can help us with, and maybe that we can help you with. Okay, so the next question I think we basically covered. It was about valuable skills. We got into that. So maybe you can switch a bit to most of you, in fact, you're pretty much all working in industry, and some of you directly involved with hiring and with overseeing engineering teams. So what do you think the sort of the trends or the experiences that our students should be focusing on? What do you think is important for a student graduating either with a BS or with a PhD to think about for their next steps, in particular in your case, in industry? Many faculty are very skilled at advising students about research and academic careers, but in industry, I think your feedback would be very helpful. So what do you see as it says trends here, but what skills do you think students should be really thinking about in terms of their next steps? Who wants to go?
Sure.
Go for it, Wayne.
It's a good question. You probably think I'm going to say AI, but I'm not. For me, I think in industry, I've had the privilege to work with some amazing people in industry, top, people very top talent individuals. And the one thing I see from them, and it is high value for myself, is focusing on the fundamentals. So maybe just as you were saying, when you're in industry, you're going to be working with lots of different engineers and scientists and people of different backgrounds. And I've always found that focusing on the fundamentals, meaning the basics in certain competencies, whether it's electrical engineering or aerospace or whatever, it's the basics that help me decipher basically the truth out of the not so true. And so having a firm grasp on fundamental principles, I think has been invaluable, continues to be.
Yeah, if I may, if I may add to build upon what Wayne was alluding to, one of the things that I have seen in my career in industry, those who have been very successful in industry, there is a very unique quality in them, and you can actually relate this quality to lots of entrepreneurs today. One of the things that they do very well is they are able to assimilate multiple fields of knowledge, bring them together in a very quick go-to-market manner, and monetize it. So I think that ability that you can probably say, okay, you don't need to be an expert in everything, but you got to know enough that you are not going to do damage. You need to know enough that you can really find what is the unique value that particular item or field is giving you, and monetizing it, stitching it all together and bringing it to the market quickly. That is an art, and people who have that art in the industry are the ones who are most successful in industry.
It's funny, I was going to say something, maybe not as eloquently as you, but I've found so many of my peers in mechanical undergrads were really like jacks of all trades, like could pick up any skill. Really broad, but generally really apt at picking up new things. And so I could always tell, I could always pick out a mechanical versus someone else, because it's like they've not deep in any one thing, but really broad, can pick up stuff. But when I put my investor hat on and hiring hat, I constantly recommend undergrads to learn like the soft side of work, like go learn to be a professional, and get paid to do it, which is the opposite of school, right? We get, go get paid to learn how to manage teams and how to hire and make bad hires, right? Therefore, then you learn have to fire. It's better to do it as quickly as possible at a place that will give you a support system to teach you, here's how to do that. Here's what we do when a team doesn't work out. Because it's going to happen again, for sure, in the rest of your life. And as an entrepreneur, as an investor now, I would rather you have already learned that as opposed to learn that on our dime when we invest in you as your first time learning everything. And so typically I'm always pushing undergraduates to go get as much work experience before venturing into starting their own company or something like that. There's no rush to start something, and so go learn with other people who have already honed some of those crafts, for sure.
Yeah, I think one thing I think collectively we're saying pretty much soft skills. That's one thing that came up in my mind is as a employer, when you see resumes, everyone can have really amazing credentials on your resume, but what stands out is how do you show that you can learn fast, on your resume, right? And in an interview, it's actually quite easy to see when you ask the questions, to show your character and to let the hiring manager know that you can work with people. You have the people skills. You can relate to people and work in teams with a diverse group. How do you manage? Everybody has a slightly different personality. How do you manage that? And that, to me, it's kind of the winning ticket. I can always teach you or get you groomed into a good engineer, but soft skills that you can obtain through schools, through activity, through clubs, it's not something that you can obtain in a day, right? So that's always something fun to see. Who can be the leader, who can be the team player on top of all the amazing credentials you can get from school.
Yeah, soft skills are a big one for me as well. I also will say, I don't know if we've popularized or modernized the idea that even if you have a mechanical engineering undergrad, I kind of expect some level of programming capability, like Python, C++, something that's not MATLAB. MATLAB, you can do a lot of stuff, but I have been a MATLAB programmer, and I understand the fault there. I graduated from that, but I definitely look for that as like a key skill, and I think some of the mechanical engineers I've seen lately don't realize that I'm looking for it. And I guess amidst all these things, I'm looking for a good amount of experience, but I'm also looking for people who are just motivated and excited to talk to me about what opportunities I have. People don't major in the kind of technology I make. You come in with a thrust, and I don't expect anyone to know everything about what I want, what I'm trying to build, but I do want people who are really enthusiastic about what we're talking about. And so when we talk about their past experiences and their past internships, my hope is that they've gone and done something they like doing so that they can articulate that passion to me, and I can tell, hey, is this going to be fulfilling for you? Because I don't want to hire engineers and then have them be sad in the corner because they don't like what they're building. That doesn't help me. It'll make their work product better if they love it, and I want to know how much they love what they do.
We should all love what we do.
I mean, you don't have to love every part, but
I don't love every part of what I do. But I love a lot of it. Okay, any more comments about these trends or skills that you feel will be valuable for students? I think that was extremely broad and helpful and interesting to understand this combination of fundamentals for soft skills and enthusiasm. Okay, we've got a few minutes left, and so I thought I could ask a question here, which is to do with how do you see ways to build bridges between MAE and alums? What can MAE do for the alums? How do you think the alums can interact with MAE? This is an open-ended question. There's no right or wrong, but I think it's a useful thing to talk about. The Dean mentioned we live in very strange times, and so I want to make sure that we have strong links with our whole community. People are what's important, and our alums are an enormous, valuable resource, and want to make sure that they want to engage with MAE, that we can also engage with them. So any suggestions or comments about what MAE can do for alums and how you feel alums could also engage with MAE?
I think I'm going to go back to bringing back the tours back, but we are always hiring. Whether we're officially hiring or not, we're always on the lookout for great talent, right? And even if we don't have a job description, we're out there looking to meet great people. And what that means is that we should, even if we don't have an open rec, we should be bringing people on to see our workplaces every day, theoretically. Just shadow us, see what it's like through our eyes, and vice versa. See what it's like for the current student today too. So I think there's just, a tighter linkage. Oftentimes when we suddenly are hiring, it's like very transactional. It's like, oh, we're hiring, got to fill the role, do the thing, and then we go back to doing work. But I think it could be more fluid and just, doesn't have to be such a big program where you have to show up and do this big song and dance. It's just, hey, one person, come take them, take an MAE student to work day, where we all just do it one person at a time. I think we could all benefit a lot more. I think the students could benefit a lot from learning what is being built in San Diego, because I don't think we actually realize that there's so many cool things at such wide variety, from ocean, space, down at the chip level. And I think just that exposure would be really, if we could do that. I don't have the perfect solution, but I've been working on it for 10 years, to be honest. Just exposure of knowing what is capable, what's being built locally, so we can keep the talent local. I'm all for that too.
That's very interesting ideas. We'll be taking notes and getting back to you. Other suggestions or ideas? This is
I'll
extremely
take a
useful.
student tomorrow if you want.
Okay.
Start it.
Yeah, so if I may add, I mean, there are great initiatives across UCSD in, alum engagement, TIP program or CAP program. I mean, those are great initiatives. I saw Will somewhere, right there you are. But I think one area, I mean, as much of course, I want students to go out and, experience the industry, which we do a good job. But I think I see one area that I feel like we can really do more. And that is, any university, honestly, any UC university, any of these schools, they have talent within the four walls, which is actually untapped. I think if industry can get a glimpse of it, a deep understanding of that talent that resides within those four walls, they fully understand, appreciate, leverage it, I think we can really take this to the next level. And, that's where I would say, can MAE, organizations like MAE, can they become a little bit more outgoing? Can they go out and say, look, here, I have a DER lab, for example, Jan's lab, phenomenal lab, great infrastructure. But I promise you, there are many electrical engineers in San Diego who don't know that there is a DER lab existing, right? So how can we make sure that we have an amazing CER, Center of Energy Research? How many of folks know about this and they can leverage what is happening? So I'm just trying to give some examples here, not picking on these labs here, but I'm trying to say is that can we be a little bit more outward focused and start pulling industry and say, hey, will you be interested in something like this? Can you work with us? And I'm sure you will find some alum who can become your sponsor in that industry space and can help you connect.
Let me build on that based on what I said, then you said, to see it come together, because I think you're right. Like, when I see, I'm out in the industry looking at what's new and exciting in sensor technology, especially in diabetes, glucose, and insulin, and I go and talk to Tandem Diabetes, Dexcom, and the spin-out startups that have come from there, and they all point back to Joe Wang's lab here on campus, where they're just sitting and watching for talent to spin out. And we could be, have these sub-segments where we're gathering industry, academic, and up-and-coming technology, and whether it's symposiums or just really casual happy hours, but just the convergence of that, where industry is being taught, here are like superstars, and vice versa. I think that's kind of a good way to be doing that for sure, and teaching industry what labs to be looking for, because the university is going to always say all of our labs are fantastic, right? But
that's correct.
Dexcom, but industries no, and definitely deep tech investors, they go wander halls of universities and they know which ones to go and be like, when's their next paper coming out, kind of thing as well too. So I like your points there.
Other suggestions or comments?
Yeah, I think co-ops was a thing when I was in school. I'm not sure it's still a thing here. That would be actually a really interesting thing, because when I would still, had openings for internships for summer interns. I was inquiring about co-ops opportunity where students can try out how is it going to be like working in a consumer product world that is fast-paced, go to market, it's the thing, but also get credits for. So I think, it would be great to bring that back, and I think it will motivate students to kind of explore options outside of the university.
Yeah, those are still on the books, but we need to do a bit of revival after COVID. It was a bit confusing. Wayne or Rachel? Let me pick on you last two comments.
I think I personally have had a great deal of success with bringing ideas to campus. So I think to the point of the department being more outgoing would probably be tremendously helpful stimulation for me to continue to bring the goodness. Northrop's done mentorship programs here. I've done networking happy hours at the Jacob School level. But it would be cool to kind of have some more targeted engagement with a department that, really made me who I am. I think that there's a lot of really goodness. And I think, I want to hire great people out of MAE, but I also value just the holistic community and networking, because in 10 years they could be they could be my boss while I'm trying to make something amazing, and they say, hey, I remember you, you did my resume review, and we have this like connection that, you know, based on UC San Diego that I think is really cool. I had another thought, but I'll hand it over to you because I think I lost it also.
That's okay. I'll, when you get it, circle back. The I think collectively what I hear from the discussion is, and I summarize it like this maybe. So at our company, we work with a number of universities, but we have UCSD and top tier engineering school in our backyard, so close. Yeah. And I would like to see that we, whatever it is, like reduce the bureaucracy or something that gets in the way to make it just a very simple interaction with a high level of communication. We have a group of MAE students coming out, I think next week, just off the cuff, come out and have a look around. And I think we need to get more at that level is what I'm hearing from everyone. And I think we can get ahead of these other models where, you know, where you're reaching out much further to try and connect to other universities.
Thank you. And Rachel, has your thought come back?
You know, I think she's gone, but
she's
I'll share
okay. So it's now 3 o'clock, so I'd like to wrap this up. Maybe I can just sort of bundle it together and say that my take-home lesson, and thank you for your time, is to talk to you all again about some practical ways to go forward, maybe in my office at some point, which is not a scary place at all. So I hope you'll join me in thanking our alum panel for their efforts and discussion. I found that very valuable and stimulating. All right, so I have a few housekeeping things. Is there another slide? There was another slide. Here we go. So very briefly, there's a break now to allow you to go to the EBU2 courtyard. There should be some signs. From the courtyard, there are some lab tours. There were sign-ups for those. I am not an expert on what happens if you would like to go on a tour that's full up, but please listen to the tour leaders to make sure we don't get problems with fire marshals and too many people in different labs. We have a number of different labs. There is a poster session with student groups. They've assembled some posters, and there are also some student organizations who are in the courtyard. Is there another? I thought there was another button after that. Whoops, we lost the other talk. Oh, here we go. Right, so enjoy the rest of the day. It won't be so formal. The reception is from 4:15 to 5:15 in the courtyard, and we do hope that you will stay engaged with MAE. Here are some of the social media links, and Katie is always happy to hear from alums, as am I. Is this it, or is there anything more? I think that is it. So at this point, I will say thank you. I hope to see a number of you at the reception. I'd like to thank all the speakers and all of you for coming, and I hope you found this a rewarding and exciting day. I've certainly very much enjoyed it, even in my MC role. And so thank you once again.
Thank you.